Hello students, uh, I welcome you all, and yes, uh, I have started with a session on the revision course of CVS, RS, CNS and kidney today. For all the students, it's going to be a marathon session. Don't have to mention your college stream or something like that. It's okay, but good you have joined, and it's a mixed session for all the students, not only from our college but from other colleges also. So uh, we will be starting with certain MCQs. We'll be solving some MCQs and also we'll be discussing the concept behind those MCQs. Just as feedback, am I audible and visible to all of you? Yes. Am I audible and visible to all of you students? I would like to know whether I am audible and visible to all of you. Oh, great, great. So we still have a chat box option working, and yes, you can post your questions intermittently when I will ask you to post your questions, because once I will move on to the screen share mode, I won't be able to see the chat box immediately. So what we will do is, after every 25 to 20 minutes 30 minutes, we'll go on to the uh, chat mode, and then you can post your questions on the chat mode. Okay, so uh, are there students from my FMG group, because I have specially announced this class for my FMG students. So I'm just waiting if my FMG students have whether started joining in. Can I have a hello or hi from my FMG students? Just for a second choice, I want to have my FMG students coming into picture. Just hold on for a second. I am just letting the things to be in flow. We will be starting with the system on CVS. So I'll be showing you the MCQs on CVS. We'll be solving those MCQs, and we'll try to understand the basics behind those MCQs. All right. So yes, here we are there with our MCQs on CVS, and hello. Are you all my FMG students? Because I wanted to know whether my FMG students have joined in. That's what my great. Okay, great. So the first topic, the first chapter we'll be starting is with the CVS. All right. In CVS, let me tell you, we'll be discussing cardiac cycle, conductive system of the heart, ECG, blood pressure, and also we'll be discussing the cardiovascular changes during exercise and the regulatory mechanism of the heart. So let us solve the MCQs first. And I hope my screen is visible to all of you. Yes. Let's turn on for a second. Let me make the arrangements here. Okay, so the first MCQ is the true statement regarding okay, we'll solve the MCQs and then we'll go for the we'll solve the MCQs first and then we'll move on to the part of chats box or MCQs and concepts. The first MCQ, true statement regarding atrial depolarization. Right atrium excites ahead of left atrium excites ahead of right atrium. Both the atria excites simultaneously or depends upon the atrial size. What are your answers? Please start posting your answers. What do you think is the answer for the first MCQ? The true statement regarding atrial depolarization. The right atrium excites before left atrium excites before right atrium. Both the atria excite simultaneously or it depends upon the atrial size. Yes, I'm getting the answers flowing in. So yes, please start posting your answers on the chat box. A, B, C, D. Which option will you choose? Okay, I'm getting maximum answer as both atria excite simultaneously. Is this answer for everyone? Yes, I'm still waiting. Kindly start typing the answers on the chat box. Okay, that's great. I have got many responses from the students. Okay, the right answer here is right atrium excites ahead of left atrium. Do you know why? If you look in the conductive system of the heart, the SA node is situated in the right atria. Remember, the SA node is situated in the right atria, and since excitation starts from SA node and then spreads to the corresponding chambers, the first one to excite, remember, right atrium is the first one to get excited, and then simultaneously both the atria will excite. So the right atria excite just before left atrium. Remember, the right atrium excites just before left atrium. So answer A, option A is the right option. Right atrium excites just before left atrium. Now I will add one more point here. There are three bundle branches which actually supply the impulse from right atrium to the left atrium. Okay, I'll just start one more thing. I'm sharing the whiteboard also. I hope whiteboard is also visible to all of you. Okay, so yeah, that's great. So I can explain the things simultaneously. Now see, for this MCQ, the correct option is right atrium excites just before left atrium. And please remember, from SA node, the impulse travel to the AV node via three bundle branches. There are three bundle branches which carry the impulse from SA node to AV node. Okay, these three bundle branches are known as anterior, middle or intermediate, and posterior. There are three bundle branches: anterior, middle, and posterior. The anterior bundle branch is known as Bachmann's bundle, the anterior Bachmann's bundle. The middle is Wenckebach bundle, and the posterior is Thorel's bundle. There are three bundle branches: anterior, middle, and posterior. All the three bundle branches, they are actually situated right in the right atrium. One of these three, A, M and P, or Bachmann, Wenckebach and Thorel, one of these carry the impulse to the left atria. Can you tell me which one of these, Bachmann's, Wenckebach and Thorel's, which one of these three carries the impulse to the left atrium? Yes, can you tell me which one of these three carries the impulse to the left atrium? Which one of these three carries the impulse to the left atrium? Yes. Which one of these three carry the impulse to the left atrium? The answer is yes. That's great. The answer is the anterior Bachmann's bundle carries the impulse to the left atria. So remember, there are three bundle branches from SN node to AV node: Bachmann's bundle, Wenckebach bundle, and Thorel's bundle, and the anterior Bachmann's bundle, it carries the impulse from right atrium to left atrium. Okay. Also please remember, there is one more bundle branch which actually goes from SN node directly to ventricles bypassing the AV node. This is a aberrant bundle branch or abnormal bundle branch, and this abnormal bundle branch is known as bundle of Kent. This bundle branch is known as bundle of Kent, and this bundle of Kent actually gives rise to a type of condition known as WPW syndrome, that is Wolff-Parkinson-White syndrome. In this condition, the impulse bypass AV node and directly reaches from SN node to ventricles, because of which the PR interval in ECG decreases. There is a decrease in PR interval. Remember, we are going to discuss ECG also, and also the QRS complex widens. It widens. So there are the three typical features of bundle of Kent. Let us go to the next MCQ. Yes, that's very right. Yes, Vivek, very right. WPW syndrome. Bachmann's bundle is yes. So next MCQ. The following statement is not true. About myosin heavy chain kinase. Which of the following statement is not true about myosin heavy chain kinase in cardiac muscle fibers? Alpha MHC has higher myosin ATPase activity. Beta MHC has higher myosin ATPase activity. Alpha MHC predominates in atria. Beta MHC predominates in ventricles. Now it is one of the trick question. I want you to answer the right option here. What do you think will be the right option here? Right answer. Which of the following statement is not true? You are supposed to answer not true. So three statements are right. One statement is not right. I want you to answer that statement. Which statement do you think is not right in the following condition? Yes. Please answer on the chat box. I am not getting answers. Is there any problem with the chat box? Let me know. Okay, I have got started answers coming in. There is a mixed response. I am happy with that. Yes. See, it's a trick question. Remember, in these four options, two options are exactly opposite and the remaining two options are quite common. So the point here is you need to identify which two options are right and which two options are out. First go for 50-50 option and then you should go for the right and wrong answers. So what do you think will be the right answer here? Yes, please. So the answer here is beta MHC has higher myosin ATPase activity is the false statement. It's a false statement. It's not a true statement. See how to get the answer. There are four statements A, B, C and D. In these four statements, you see A and B, they have just changed alpha and beta here. Okay. Whereas if you see on C and D, they have actually mentioned alpha MHC predominates in atria and beta MHC predominates in ventricles. So if there are two different types of chambers, atria and ventricles, and they have different timings of contractility, means they must be having different types of myosin heavy chain kinases. So the C and D statements are always true here. When C and D statements are true, then we have only false statements from A and B. And you can see in A and B, alpha MHC is written as higher and beta MHC also written as higher. How can we have both the statements as higher and higher? One of them has to be false. So definitely your answer lies between A and B. Your answer lies between A and B. And if we consider C and D as the right thing, then alpha MHC has higher myosin ATPase activity and atria always contracts first before ventricles. Then A is going along with C, but B is not going along with D. So the right option means not true statement is beta MHC has higher myosin ATPase activity. It should be beta MHC has lower myosin ATPase activity. That's why the option B is the answer here. The option B is the answer here. I know it's quite difficult, but it just requires some amount of knack. 50-50 options. You should go for first 50-50 options and then you should be able to answer the things. Next question, which of the following is not a rapidly depolarizing fiber? Which of the following is not a rapidly depolarizing fibers? Yes, SA node, Purkinje fibers, atriomyocardial fibers, ventricular myocardial fibers. Which of the following is not a rapidly depolarizing fibers? Slow depolarizing fibers. Slow. Which of the following is a slow depolarizing fibers? Yes. Can I have the answers from the students? Yes, students. Okay, Chetna has started answer. Great. Not rapidly means slow depolarizing. One of them is slow depolarizing fiber. I want you to guess the answer. The one which is a slow depolarizing fiber. Okay. After this MCQ, I will be discussing something on conducting system of the heart in quite more detail. Alright, in quite more detail. Alright. See, the right answer here is actually not a rapidly means slow depolarizing. Please remember, not rapidly means slow depolarizing fibers. Slow. And slow depolarizing fibers means the depolarization is slow. Remember, and rapid means a rapid depolarization. So which of these shows a slow depolarization? The answer here is yes. Still any more people to answer? Okay, the answer here is A. SA node is a slow depolarizing fiber. Remember, SA node is the slow depolarization fiber. Let us go with the concept here. See, there are two types of action potentials in the heart. One action potential is action potential in SA node and AV node, and other one is action potential in the Purkinje fibers, ventricular muscle fibers, and also we have the atrial fibers. Remember. Now what is the difference here? Remember, on the basis of their excitability and their conduction, the fibers are divided in two types. One is the slow response type fibers and other one are fast response type fibers. The slow response type means their depolarization is slow. Whereas for fast response type, the depolarization is fast. First point. Second point, in slow response type, the depolarization occurs because of calcium ions, whereas here it occurs because of which ions? Can I have the answer here? In the fast response type, what do you think will be the ion for depolarization? Which ion causes depolarization in fast response type? The answer here is yes, it is sodium ion. It is sodium which causes depolarization in fast response type. Next, in slow response type, yes, very good, Ria, the repolarization is fast. Remember, the repolarization is fast, but here in fast response type, the repolarization is slow. There is a slow repolarization in fast response type, but fast repolarization in slow response type. Let me give a simple example here. Suppose if there are four individuals running on a race track, SA node, bundle of E's, Purkinje fibers, ventricular muscle fibers. Okay. Now all four of them, they are running and they all four fall down at the same place, at the same line. Now if all four have fallen at the same line, the one who will win the race is the one who will recover fast, the one who will get up fast for the next run. So in this case, SA node recovers fast from as compared to all other muscle or excitable tissues. Since SA node recovers fastest, it has the tendency or potential to go for next action potential immediately before any other fiber. So SA node is pacemaker not because of slow depolarization. SA node is pacemaker because of its fastest repolarization. Please remember this point. SA node is the pacemaker of the heart because of fastest repolarization. Okay, so this is one of the interesting point here. How does the action potential looks like? Remember, the slow response type, the action potential comprises of two things. One is pre-potential and the other one is depolarization. There are two phases here, pre-potential and depolarization. Whereas here it is rapid depolarization. It is only one phase. How does it occur? See, in pacemaker cells, in SA node and AV node, look at the way the pacemaker cells go for action potential. Okay. Initially, the RMP of pacemaker cell is minus 65 millivolts. RMP of pacemaker cell is minus 65 millivolt. So they go from RMP to threshold slowly, but they go automatically. It is automatic. They automatically go from RMP to threshold. RMP is resting membrane potential. So from resting membrane potential to threshold, they go automatically. So if -65 is the RMP to threshold, they go automatically. And there are three phases here. Remember, there are three phases from RMP to threshold. And the fourth phase causes actual depolarization in slow response type, that is SNOD. Okay, what we are discussing is the ionic basis of action potential in ionic basis of action potential in pacemaker cells or SNOD and AV node. Okay, so this is the way they depolarize, and then we have again repolarization, and again they go automatically from RMP to threshold for next depolarization. In this way they keep on going from RMP to threshold, automatic excitation, and then they go for repolarization. What is the mechanism here? Yes, SA node and EV node both has slow depolarization, but the time is different. Time is different means SA node repolarizes fast, AV node repolarizes later. Okay, SA node repolarizes fast, AV node repolarizes later. Repolarization is quite slower. Okay, so what are the three events? If I ask you which one is the first event to occur, in pre-potential? The 1, 2, 3 is known as pre-potential. The 1, 2 and 3 are known as pre-potential, whereas this one is known as depolarization and this one is known as repolarization. Okay, repolarization is always because of potassium ion. Remember, the repolarization is always because of potassium ion. Now I want to know one thing here. What do you think? Yes, Mani 7. The SA node and AV node both has slow depolarization, but AV node repolarization is slightly later than SA node repolarization. So SA node is the fastest to repolarize and hence first one to get depolarized earlier than any other tissue in the heart. The first event to occur in pre-potential is potassium ion. What happens? See, at the end of repolarization, remember, at the end of repolarization, the potassium channels they close. At the end of repolarization, the potassium channels they close. Since potassium channels close, the potassium won't go out. If the potassium is not going out, see, try to understand this point. The repolarization is because of exit of potassium ions. Alright, via potassium channels. Now the potassium channels are time gated in the type of SA node. So at the end of repolarization, the potassium channels close. The moment potassium channel close, the potassium efflux is stopped. The moment potassium efflux stops, the potassium accumulates inside the cell. This potassium accumulation develops a positive charge inside the cell. This positive charge causes the first phase of pre-potential. It is because of closure of potassium channels. Remember, the first phase in pre-potential or pacemaker potential is closure of potassium channel. Now because potassium accumulates, the membrane goes from -65 to less negative value, say -60 or something like that. Now what happens? Immediately the second phase starts. In the second phase, remember, the sodium channels open and sodium starts entering the cell. And sodium entry makes the membrane more positive. Now since this sodium entry is automatic, it is also called a sodium funny current. It is also called a sodium funny current. So the second part of pre-potential is because of sodium entry, called as sodium funny current. It is called as opening of sodium channels, which makes the membrane more positive, and the phase 2 is pre-potential of sodium ions. Now the moment membrane becomes more positive because of sodium entry, the phase 3 starts. In phase 3 what happens? Remember, in phase 3 what happens? the calcium channels open. Because of less negative value, the calcium channels open and calcium starts entering the cell. And which type of calcium channels? The T type of calcium channels. Which type of calcium channels? The T type of calcium channels, known as calcium T channels, transient channels. So opening of calcium T channels. So there are three events in pre-potential. Remember, there are three events in pre-potential: closure of potassium channel, opening of sodium channel, sodium funny current, opening of calcium T channel, and entry of calcium ions. I repeat, there are three events in pre-potential. First, closure of potassium channel. Second, opening of sodium channel. Third, opening of calcium T channel. Okay, there are three events in pre-potential. And the moment calcium T channel is open, the calcium enters the cell, makes the membrane more positive. Now the membrane has reached to the threshold. The moment membrane reaches threshold, what happens? Calcium L channels open. The calcium L channels open and completely depolarizes the membrane. The L stands for long-lasting channels. So there are two types of calcium channels. One is calcium T channels, another one is calcium L channels. Okay, is it clear to all of you till this point? May I know, am I going right? Am I going fine with all of you? Able to understand everything here? The pace is fine here? Yes? Is everything fine here? Is everything going fine till now? Yes, Kesar. Yes, you are right. Sodium funny current, the one point, yes, which Kesar has raised. Definitely, the channel of sodium ions, which is opening at this point, these channels, these sodium channels of funny current, they are called as HCN gated sodium channel. HCN gated sodium channel. And these HCN gated sodium channel are actually known as hyperpolarization cyclic nucleotide gated sodium channel. I repeat, the HCN gated sodium channel, which cause sodium funny current, they are actually hyperpolarization cyclic AMP nucleotide gated channels, which open when the cell is not completely depolarized. That's why it is called as sodium funny current. Okay, so I'm happy students are, yes, definitely paying attention, and yes, that's great. Please make maximum use of chat box, because it is the only way I can interact with you right now. Okay, it's the only way I can interact with right now, all of you. The chat box is the only way which I can interact with right now. Great. So yes, now please try to understand the application part of it. Since we know the phases, there are 4 phases now in the action potential of pacemaker cell. There are 4 things which are happening: closure of potassium channel, opening of sodium channel, opening of calcium T channel, and opening of calcium L channel. All these 4 events, one by one, they cause the membrane to depolarize. When the membrane depolarizes, an action potential is generated, which causes remaining part of the heart to get excited. The moment depolarization gets over, potassium exit continues, and the potassium exit causes repolarization. Now there are 2 things: the sympathetic stimulation increases the cardiac activity, and parasympathetic stimulation decreases the cardiac activity. How does it occur? Here? See, it's very interesting. This is the most interesting part. Whenever you stimulate sympathetic nerve, the sympathetic stimulation, remember, the sympathetic stimulation it causes potassium channel to remain open for a longer duration. The parasympathetic stimulation causes potassium channel to open for a longer duration. The moment potassium channel remains open for a longer duration, the potassium exit continues, potassium keeps on moving out and the slope of free potential decreases. Remember, the slope of free potential decreases because of parasympathetic stimulation. So parasympathetic stimulation decreases the slope of free potential. You have to remember this word for your exam point of view. The parasympathetic stimulation decreases the slope of free potential because it keeps the potassium channels open. Alright. Yes, Dharmendra, sorry, decreased. If you see, the response will be decreased. You can see, because the slope decreases, the next AP will be coming later and hence it inhibits the heart. So parasympathetic causes inhibition by decreasing the slope of free potential. On the other hand, the sympathetic stimulation, remember, on the other hand, the sympathetic stimulation, it increases the slope of free potential. By increasing the slope of free potential, the cardiac excitation occurs earlier and that causes increase in the heart rate. So sympathetic increases cardiac activity and parasympathetic decreases cardiac activity. Alright, so remember these 2 points here. And how does sympathetic works? The sympathetic works by early closure of potassium channel and causing increase in the slope of free potential. So I repeat again, sympathetic stimulation causes early closure of potassium channel. Parasympathetic stimulation causes late closure of potassium channel. Sympathetic stimulation increases slope of free potential and parasympathetic decreases the slope of free potential. Sympathetic increases slope of free potential and parasympathetic decreases slope of free potential. Please remember these 2 points. They are very interesting points here as far as the ionic basis of action potential is concerned. Moving to the next point, let us go to the next MCQ here. I hope I have answered this already. Parasympathetic is for keeping the gas chaser. Parasympathetic is responsible for keeping the potassium channels open, and that's why the potassium keeps on leaking out. And because the potassium keeps on leaking out, it causes the free potential slope to decrease and the membrane doesn't excite earlier. Let us go to the next MCQ. Fourth, which of the following is fastest repolarizing? Yes, now everybody should be able to answer. The fastest repolarizing fiber here is, yes, please everybody answer for this MCQ. The fastest repolarizing cells or fiber is for SA node, AV node, bundle of cells, Purkinje fiber. We have just answered this question here. We have just answered this question in the concept. Oh, please don't give me wrong answer now. Fastest repolarizing. Just now we have discussed why SA node is fastest. Yes, please correct your answer. The answer is SA node. Remember, we have just discussed here. If you could see, and we have mentioned in the classification also, the repolarization is fast and here repolarization is slow. SA node is the fastest repolarizing fiber. SA node is the fastest repolarizing fiber. If you want to understand how does this work, let me draw the action potential of all 4 types of fiber. Let us start with SA node. The SA node depolarizes and then repolarizes. Okay, then you have AV node. The AV node start a little later, depolarizes and then repolarizes. Then you have bundle of His. Bundle of His has a quite faster depolarization but slow repolarization. Then you have, after a bundle of His, you can say ventricular muscle fibers or atrial muscle fibers. So this will be for atrial muscle fiber or Purkinje fibers. In this way, you have 4 types of tissue: SA node, AV node, you can say bundle of His, and Purkinje fibers, or you can say ventricular muscle fibers. So you can see the first one to depolarize is SA node, but first one to repolarize is also SA node. Second one to repolarize is your AV node. third one to repolarize is your bundle of E's, and the fourth one to repolarize your Purkinje fibers or ventricular muscle fibers. So the last one to repolarize is your ventricular muscle fibers. Yes, Mani, any doubts here? Any doubts, Mani? Please tell me why you are so sad. Mani is making sad face. I think the Mani must have answered the thing wrong. Yes, Mani? Okay. The answer is SA node is the fastest repolarizing fiber. Alright. Going to the next MCQ. Conduction velocity is fastest in the fastest fiber, the fastest conduction velocity. And the options are A, B, C, D. SA node, AV node, bundle of E's and Purkinje fibers. Okay, man. Thank you. Conduction velocity fastest. Can you give the answer for this one? Conduction velocity is fastest in SA node, AV node, bundle of E's and Purkinje fibers. Yes. Yes, very good. Very good. The answer is yes. Everybody answer it right now. Purkinje fibers are the fastest fibers. The fastest are Purkinje fibers. That's perfect. And the slowest one. Can I have the slowest one here now? If all of you are done with fastest, can you mention the slowest fiber here? Slowest conduction velocity. After fastest, I would like to know the slowest conduction velocity also. The slowest is, yes. After fastest, if I'd like to ask you which one is the slowest. Thank you, Ria, Yashi, Vishakha, and yes, sir. Fastest conduction velocity. Purkinje fibers have the fastest conduction velocity. Yes, B is slowest. AV node is the slowest fiber. Slowest is AV node. Let us write down the velocities. Here. For SA node, it is 0.05 meters per second. For AV node, it is 0.02 to 0.05 meter per second. For bundle of E's, it is almost 1 meter per second, the conduction velocity. And for Purkinje fibers, yes, for Purkinje fibers, the velocity is, that's perfect. I'm waiting for the answers. For Purkinje fiber, the velocity is, yes, I'm so happy that students are very actively answering, but some students have left the chat box. There were 80 students in the initial part. Now there are 70 students almost, and yes, yes, 4, that's perfect. Everybody answered right. 4 meters per second, the fastest is, yes, perfect. Fastest velocity is Purkinje, slowest is your, yes, AV node. That's perfect. Now let us go to the sixth question. The first event to occur in pre-potential. We have just discussed this question. So nice, so many things we have discussed, and you are able to answer all these things right. That's what my aim is. We discuss some small concept, and on one concept you are able to answer so many questions. That's the whole point. If you are able to understand the concept, one good concept gives you the ability to solve 5, 10 or 15 MCQs actually right. So the sixth question, the first event to occur in pre-potential or pacemaker potential is sodium funny current, decline of potassium current, activation of calcium T channels, or activation of calcium L channels. No, okay sir, it is 4 meters per second, not 0.4 meter per second. Yes. No, Dharmendra, I beg to differ here. Just now we have discussed. Yes, please. No, how can it be sodium funny current? We have just discussed the first event. If you could see the, if you could see the pre-potential here, we have just discussed pre-potential. Can you see pre-potential? 1, 2, 3, 4. Please look at the diagram. What do you think is the first event to occur? Yes. That's perfect. Few students have answered it right. Yes. That's perfect. That's perfect. Now, yes. Many students have answered it right. No, not C, Dharmendra. If you can see, potassium is the first event to occur. And the question is the first event to occur in pre-potential. So the answer is decline of potassium current is the first event to occur in pre-potential. B. The right answer is B. The right option is B. That's perfect. That's perfect. Right option is B. Decline of potassium current is the first event to occur. Yes, I can see. Yes. Yes, Shifal, it's B. Absolutely B. Mohammed, you please correct your answer. It's B. And yes, closure of potassium, answer it right. I can see. Yes, sodium, potassium, that's perfect, that's perfect. Yes, yes, that's fine. Okay, so nice to have you all answering the right option here. Next, yes, the activation of sodium funny current. The activation of sodium funny current or F channel or HCN gated channel occurs due to depolarization, repolarization, hyperpolarization, or resting potential. Yes, Shabnam, you are absolutely right here. For sixth option, the answer is yes, B. Seventh question, we are on to seventh question. The activation of sodium funny current occurs because of D, Re, hyper, or HCN. If you can see, the name is hyperpolarization cyclic nucleotide gated channels, HCN gated channels. So HCN gated channel means what? Hyperpolarization cyclic nucleotide gated channels. Yes. No, okay, sir. Seventh answer cannot be A. No, it doesn't occur during depolarization. The activation, they are asking about activation. That's what the point is. See, sodium channels, we all know that sodium channels, they have to they open on depolarization, but only in the case of cardiac muscle. Please try to understand this point. Okay, please try to understand this point. We all know that sodium channel, voltage gated sodium channel, they activated depolarization, right? We all know that voltage gated sodium channel, they activated depolarization. But in the case of pacemaker cells, the sodium channels, they behave in such a different manner that they open at a potential where they are not supposed to. Hence, they are called as hyperpolarization cyclic AMP nucleotide gated channels. So, since the word is cyclic AMP, means there are two things involved. First, they are opening at hyperpolarization, and second, these channels are not inotropic, they are metabotropic. they are using secondary messenger pathway. So they are not a usual the usual sodium channels which you are talking about, which are responsible for action potential in nerve cells or muscle cells. These are the sodium channels which are quite different, which are voltage specific, but they are opening at hyperpolarization potential, and they are cyclic AMP. They are not inotropic. Okay. It's okay. It's okay. I beg to refer that Mr. Exhibit attend. It's okay. Everybody has their own opinion. So let the things in the chat box be as usual. Let everybody will be with the natural things. No, please be. It's okay. It's absolutely fine. Okay. Everybody are free to have their own opinion. So let the things go in a smooth manner. Okay. The answer is C. The answer is C for 7th question. It's hyperpolarization. Answer is C. That is hyperpolarization. Let us go to the 8th question. Rapid depolarization. Rapid depolarization. Remember, an MCQ is asked on image-based thing, and the image-based question is, you will be shown two types of depolarization. One depolarization is like this, and the other depolarization is going to be like this. Now you will be asked which ion here and which ion here. We already know that this is calcium ion. Okay, now can you tell me which ion is going to be here? Yes. That's perfect. Yes. Thank you, Dr. Mukesh. Yes, the answer is sodium. So the point here is, remember the point here is, if there is going to be a smooth peak, then it is always calcium ion. Please remember how to identify the things here. If there is going to be a smooth peak, then it is always going to be a calcium ion. If there is going to be a spike, remember whenever we have a spike, we are always going to have a sodium ions. Whenever we have a smooth peak, we have calcium ion. Whenever we have a spike, it's going to be a sodium ion. Yes, perfect. Yes, that's very nice. Okay, let us go to the next question. Yeah, this is also simple. We have just discussed all these questions here. Slow depolarization. Now let us go for the 9th one. The slow depolarization is because of which ion? Yes, Mani. We'll discuss that also, Mani. Yes, we'll discuss that part also. I have not discussed that part yet. Plateau phase, because we have not discussed the action potential Purkinje fibers. I'm on to it. Let us first solve the MCQs at this point of time, till this point. The answer for slow depolarization. That's perfect. Now, why sodium? Krish? No, Krish, the answer is calcium. Slow depolarization. We have just discussed, Krish. Slow depolarization because of calcium ions. Alright. Yes. Okay, so yes, everybody has answered it right now. Yes, perfect. Can I have the hello from the students, those who are my FMG students in a group? Just a hello or hi, only from the FMG people, because there is something which I wanted to announce, and yes. Can I just a hello or a hi from the students who are my FMG students? Okay. Just I wanted to have, like few things which I wanted to mention here. Okay, that's great. That's great. With these many? Yes. Only these many students are there from FMG? Okay, I think others. Yes, okay, okay. Okay. Just type hi or hello so that I will. I'll have to mention something so that I should know that how many of us are actually are in contact with each other. See, the thing is what I wanted to say, what I wanted to announce here is that not only on this YouTube platform, but I'm also taking class on Unacademy, and since you have this advantage of good online learning things a bit of, so what I would request you is that you should also join the Unacademy this month, that is from 18th. There are going to be seven special classes starting from 18th of this month, where I'll be discussing MCQs and all those things also. So we are going to discuss all the MCQs here on this YouTube platform, okay, right from your college and coaching institute, and also we'll be discussing MCQs on Unacademy platform also. So take the maximum advantage of online learning. That's what my aim is. All right. So do join me on Unacademy also, and yes, you can also follow my Facebook page or YouTube channel where you will get daily updates of my daily or weekly updates of new video channel to upload. So that's great. That's great. I can see many students are listening to me, and I'm happy with that. Okay. The ninth question. Oh, ninth question. We are done with ninth question, right? Yes. Ninth question is calcium. Perfect, Shabnam. Let's go to the 10th question. Let us go to the 10th question here now. 10th question. Increase in excitability of heart is known as. Increase in the. Yes, thank you. Thank you, Amit. Thank you, Manish. Excitability of the heart. There are 4 effects: chronotropic, inotropic, dromotropic, bathmotropic. What do you think is the answer? Excitability of the heart? Yes. Perfect. Yes. Excitability of the heart is? Yes, very good. No, few students answer it right and wrong. Okay. The answer is bathmotropic. Chronotropic is the rate of excitation. Remember, it's a rate of excitation. Chronotropic. Inotropic is force of contraction. Dromotropic is conduction velocity. And bathmotropic is excitability. Remember 2 important points here again. 2 important points here. The 2 important points are sympathetic stimulation and adrenaline causes all the 4 effects positive. Sympathetic stimulation and adrenaline causes all the 4 effects positive, and parasympathetic stimulation and acetylcholine causes all the 4 effects negative. So if there is sympathetic stimulation, it is going to be positive chronotropic, positive inotropic, positive dromotropic, and positive bathmotropic. Where if it is parasympathetic stimulation, it will cause negative of all the 4 effects. Okay. So the answer here is bathmotropic. Okay. No, Sabnam, the 10th question is answer is D. Answer is D for the 10th question. Excitability of the heart is bathmotropic effect. Okay. Now, the very interesting question. True statement about ventricular excitation. Left ventricle excites ahead of right ventricle. Right ventricle excites ahead of left ventricle. Both ventricles excite simultaneously or depends upon the ventricular size. It is very important and very interesting question, because many entrance exams have these questions about the excitability and conductivity of the ventricular muscle fibers. Yes, I would like to just correct you, Shabnam. The answer is for the 10th question is the bathymetropic effect. Okay. Okay. So for the 11th, true statement about ventricular excitation. Left ventricle excitation starts ahead of right ventricle. Right ventricle excites ahead of left ventricle. Both ventricles begin to excite simultaneously or depends upon the ventricular size. Okay, Akshata has answered A. Okay, that's nice. Okay, that's nice. Okay, that's perfect. Yes, so yes, many of you answered it absolutely right. The answer is left ventricle excites ahead of right ventricle. Now what is the answer here? And we'll go to the next MCQ and then we'll go for ventricular excitation. Okay, the last part of the heart to be depolarized is, we'll go for ventricular depolarization separately again. I'll explain you the concept behind ventricular excitation. For 12th question, what do you think the 12th question? What is the answer for 12th question? Yes. What is the answer for 12th question? The last part of the heart to be depolarized is. I'll wait for more responses. Yes, yes, sir. Yes. Okay. I'm going for 12th question. The last part of the heart to be depolarized is posterobasal portion of the right ventricle, posterobasal portion of the left ventricle, endocardium of base of right ventricle, epicardium of base of left ventricle. Okay, before answering this, I will let me just throw some light on the concept here. Let us try to understand the basis of action potential in the ventricular muscle fibers. All right, like we have discussed for let us go to the action potential in the ventricles and how does it work. Okay, so first we'll discuss the action potential, basis of action potential, ionic basis of action potential in the ventricles. See, in ventricles the action potential is rapid. Okay, and there are 4 phases of action potentials: 0, 1, 2, 3 and 4. The 4th phase is actually your RMP, the steady state potential. Phase 0 is because of depolarization, is because of sodium ion voltage gated sodium channel. The phase 0 is depolarization is because of voltage gated sodium channel. Okay, phase 1 is because of 2 things. There are two reasons for phase 1. One is closure of sodium channel. Remember, sodium channels are fast channels. They open very fast and then they close very fast. So the closure of sodium channel restricts the spike potential, and the second point of phase 1 is opening of potassium channel. So there are 2 points in phase 1: closure of sodium channel and opening of potassium channel. These are the two important points for phase 1. In phase 2 what happens? In phase 2 what happens? The potassium channels remain open. The potassium channels remain open. Okay, but we also have opening of calcium channels. Opening of calcium channels. So what happens? If you look at a cell of a cardiac muscle, then calcium opening will lead calcium to come inside the cell, and the potassium channel opening will cause potassium to move out of the cell. So potassium going out and calcium coming in means the positive charges going out and positive charges coming in, means the charges are balanced. And since the charges are balanced, yes Shabnam, D is the right answer. Since the charges are balanced here, the plateau phase exists. And the advantage of plateau phase is it is called as long refractory period. Long refractory period, because of which the heart muscle never goes under tetany. The heart muscle never goes under tetany or tetanic contractions. Okay. Phase 3. Phase 3, now there are two things for phase 3 again. Number 1, the potassium channels remain open. The potassium channels remain open, but calcium channels have closed now. The calcium channels have closed. So the membrane repolarizes. And at phase 4, the voltage graded potassium channels close. Okay, the voltage graded potassium channel close, but the leaky channels remain open and RMP comes into picture. So there, I repeat again, there are in all 0 to 4 5 phases in the action potential of Purkinje fibers. Phase 0 is because of depolarization, which occurs because of sodium ions. So sodium ion causes depolarization in phase 0. Phase 1 is due to two things. Number 1, closure of sodium channels and opening of potassium channels. Because sodium channels are very fast channels, they close very fast and then they open very fast. Okay, they open very fast, they close very fast. So sodium channels starts opening, they cause depolarization and then they close. But potassium channels, they start opening slowly. So phase 1 is because of closure of sodium channel and opening of potassium channel. Now once potassium channel starts opening, the membrane starts repolarizing. But during this repolarization, the calcium channels open. And why calcium channels open? Because the heart muscle wants to contract. So calcium channels open and calcium starts entering the cell. So on one side calcium is entering for contraction and one side potassium is going out because of its repolarizing phase. So positive going out and positive coming in, these both things, they don't allow the membrane to repolarize. The membrane goes under plateau phase. Plateau phase is known as long refractory period, which prevents the heart from getting under tetany. The heart muscle never goes under tetany, even though there is a high frequency of stimulus coming to the heart. Phase 3, now when phase 2 gets over, because when the heart is contracted and relaxed, see contraction, the heart is going for contraction and it again goes for relaxation. So during relaxation, remember, the calcium channels are closed and calcium is now thrown out of the cell for relaxation, but potassium channels remain open. So calcium entry stop and potassium exit continues. So the membrane repolarizes. And that causes phase 3. Now at the end of phase 3 we have phase 4. Now in phase 4 what happens? The voltage graded potassium channels are closed, but leaky potassium channels remain open and it turns back to its RMP. It goes back to its RMP is because of potassium channels. So this is the very interesting fact that potassium channel remains open during phase 1, phase 2, phase 3 as well as phase 4. Okay, phase 1, phase 2, phase 3 and phase 4. Now coming to the next point here for 12th question, the question number 12. 11th and 12th both. If you look at the ventricular structure, the left ventricle excites ahead of right ventricle. Why? Why is it so? Why is it that left ventricle excites ahead of right ventricle? If you can look in the conducting pathways, from AV node, the bundle of His arise, and the bundle of His they first give a branch to the left ventricle, okay, which goes to interventricular septum, and then they continue to the right ventricle. So the left ventricle gets excited first, and then we have the right ventricle getting excited. So left ventricle excites first as compared to right ventricle. The left ventricular excitation occurs before right ventricle. So left ventricle excites before right ventricle. This is the first part. Now look at the way the heart excites and contract. How does the heart excites and contract? See, if you try to imagine the situation here, let me get to the full screen mode. If you look at the situation here, the the heart excites and contracts, and the contraction starts from apex to base. If you look at the ventricles like this, they are the ventricles. The heart starts contracting from the apex and then goes to the base. What happens? The blood starts moving out from the heart to the pulmonary artery and all those aorta. So ventricles have to start contracting from apex and then it should go to the base. So the first part to be getting excited is the apex. The last part to get excited is the base. Even though if you look at the apex to base, the inner part of the heart is endocardium and outer part is epicardium. So if you want to contract the heart muscle, the first one to excite and contract will be endocardium, and the later one will be epicardium. Okay, so endocardium will excite contract, endocardium will excite contract, then endocardium of base will excite contract, and epicardium of base will excite and contract. So the overall sequence is apex to base, endocardium to epicardium, apex to base, endocardium to epicardium. So in this way the heart contracts. So if you actually look at the sequence here, the sequence will be A, B, C and D. A will be the first one to get excite and contract, B will be the second one to get excite and contract, C will be the third one to excite and contract, and D will be the fourth one to excite and contract. And the D is nothing but epicardium of base of the heart. D is epicardium of base of the heart. So the actual answer, the answer here is for 12th one, the last part 2 of the heart to be depolarized. B could be the answer, but since you have this option in your MCQ, the answer is D. Alright. B could have been an answer because B is also one of the answer, but D is a better choice as compared to B. Remember, D is a better choice as compared to B. Okay, are you all clear to this point? Hyperpolarization, no, not repolarization. Repolarization is quite different. Dharmendra, we are talking about depolarization and repolarization. This is the way it is depolarizing, and look at the way it repolarizing. Yes, hyperpolarization is also hyperpolarization. Yes, ionic basis of hyperpolarization is always potassium ion, not sodium ion. Hyperpolarization is because of potassium ion. Sodium will never cause hyperpolarization because sodium, whenever sodium channels will open, sodium will always move from outside to inside. So in any of the excitable tissue, remember Dharmendra, in any of the excitable tissue, it is always potassium which is going to cause hyperpolarization. Alright. Sorry. Okay. Now if you look for repolarization, then see, in repolarization, the heart will repolarize and relax. So this is the way it will excite and contract, and this is the way it will relax and repolarize. So excitation, contraction from apex to base, and repolarization from base to apex. So the first one to repolarize will be D. I'm just giving the sequence here. The depolarization sequence is The depolarization sequence is A, B, C and D. This is the depolarization, and repolarization will be D, C, B and A. Means first to repolarize will be epicardium of base, second to repolarize will be endocardium of base, third one to repolarize will be epicardium of apex, and the fourth one to repolarize will be endocardium of apex. So DCBA is the sequence of repolarization and ABCD is the sequence of depolarization. Please remember this point. Yes, perfect. That's perfect. Let us go to the next point here. Do you know there is one drug called as digoxin digitalis? The digoxin digitalis, it causes increase in the positive ionotropy. How does digoxin digitalis causative? How does digoxin digitalis causes positive ionotropy? I want to know this point here from all of you. How does this causes positive ionotropy? See, if we look at the cardiac muscle cell, the digoxin digitalis, it binds to the sodium potassium pump. It binds to the Na plus K plus pump. My question is, it binds to which part of Na plus K plus pump? Digoxin digitalis binds to which part of Na plus K plus pump? No, something different. Yes. See what happens when the drug is given. The drug inhibits pump. The drug inhibits the pump. It binds onto the OABN binding site. It binds to the OABN binding site of the sodium potassium pump. This causes it causes the sodium potassium pump to become inhibited, and when the sodium potassium pump becomes inhibited, the outflow of sodium is decreased. Okay, and inflow of potassium also decreases. Both the things are decreased. Sodium going out and potassium coming in, both of them are decreased. Since sodium going out is affected, remember, since sodium going out is affected, the sodium outward movement with calcium inward movement, that is sodium calcium exchanger, what is called as sodium calcium exchanger, also doesn't work. Please remember one interesting point here. The sodium calcium exchanger works very typically as a secondary active transport. What happens when the pump is inhibited? When the pump is inhibited, the sodium is unable to go out. And when sodium is unable to go out, sodium is unable to come inside the cell because of force, and because sodium is unable to come inside the cell, the calcium is unable to go out. So NCX, that is sodium calcium exchanger, it stops working. It gets inhibited. Since sodium calcium exchanger gets inhibited, the calcium remains inside the cell, and this causes positive ionotropy, that is increase in force of contraction of the cardiac muscle cells. Okay. Yes, sir. Increasing cytosolic calcium by increasing the calcium inside the cell. Okay. So this is one of the interesting part here. Let us go to the ECG now. I will give a very small brief about ECG because itself is a very long, big topic. In ECG, we record the conductivity of the heart. वायर लगा दे, टीवी का वायर निकाला, वायर लगा दे, हाँ टीवी का वायर लगा दे. Yeah, we will go with the 13th question, but before, let us go to the ECG part. In ECG, we record the conduction of action potential or conduction of excitability in the heart. Yes, Mani, sodium and calcium both will increase in the heart. Yes, absolutely right. Sodium and calcium, both of them increase in the heart. See, the ECG records the direction of action potential or direction of the excitation in the heart. If you look in the ECG, we record three important points here: the right arm, left arm, and left leg. So if you look at the direction of leads, these are the leads. The one lead is from right arm to left arm, that is called as lead 1. Lead 2 is from right arm to left leg, and lead 3 is from left arm to left leg. Okay, actually originally the lead 2 was from left arm to right arm, left leg to right arm, but we have inverted it, so we make lead 2 as the equation. We change the equation here, but the main concern is how do we record this PQRST waves. That's my main concern. In ECG, we record the direction of the impulse in the heart, and in the heart the impulse always travel from atria to the base of the ventricle and to the apex. So the impulse always travel in one direction, from base to apex. The impulse in the heart always travels from base to apex. The ECG also records how the direction and in what time the impulse is reaching from one place to other place. So the time and the direction, these two things are very importantly recorded in ECG. Okay, now if you look at lead 2, the direction of lead 2 is also from base to apex. Now the rule is, if the impulse travel in the same direction of the lead and current travel in the same direction, you will have an upward deflection. If the current travels in opposite direction, you will have a downward deflection. If the current travels towards the lead, we will have an upward deflection. If the current travels away from the lead, we will have a downward deflection. Remember these four rules here. If the direction of the current or conduction of the heart impulse is in the direction of the lead, we will have an upward recording. If the current is moving away from the lead, opposite, we will have a downward deflection. If the current is moving toward the lead, you will have an upward deflection. So based on this point, you all need to tell me, if the current is traveling, if the conduction is occurring from SA node to AV node, the direction of the current is in same way, in the same direction, right? From SA node to AV node, it is in the same direction of the lead. What we are going to record here? What are we going to record in the ECG? Upward or downward deflection? Yes? What are we going to record here? Upward deflection or downward deflection? Yes, students? Can anybody? If we record the impulse direction and ECG recording, we will see both of them are in same direction, so we will have a upward deflection, P wave. P wave is the upward deflection, and there is a time difference from all atria to get excited and the impulse coming to the AV node, so you have a interval, slightly interval. Okay, both of them are in same direction. Lead 2, we are recording lead 2, so it will be upward deflection. Very good. Now look at the second point. Now from AV node, the impulse travel to bundle of His. Now this direction is quite away from the lead 2, so you have a Q wave recording like this, because the impulse in the left atria is getting excited first, so impulse is going away from the lead 2, we have a Q wave. But then all the impulse, they travel right into the ventricles, we have a R wave. Okay, till apex, from base to apex, all the impulse, they travel from base to apex, so we have a R wave. Then what happens? All the impulse, they go from apex to base. All the impulse, they go from apex to base, right? If they go from apex to base, then you are going to have a S wave. S wave, because all the impulses, they go from apex to base, so direction is opposite. The direction is opposite as compared to other waves. So Q wave, R wave and S wave, and finally it comes back to its baseline. So QRS complex gives ventricular depolarization. So now you have two things important. P wave is atrial depolarization. QRS complex is ventricular depolarization. Alright. P wave is atrial depolarization. QRS complex is ventricular depolarization. And after the ventricle get depolarized, they also get repolarized. So the repolarization in the ventricle is from base to apex. If you could remember, the repolarization in the ventricle is from base to apex. So you have a T wave getting upward deflection because they are in the same direction. Okay, they are in the same direction. So you have a T wave. So T wave is ventricular repolarization. This is ventricular depolarization. Okay, I hope you are getting this point clear. So P wave is atrial depolarization, QRS complex is ventricular depolarization, T wave is ventricular repolarization. Is this all point clear to all of you? Is this all clear to all of you? Yes, dear students. Now let us integrate one interesting point here. Let us integrate. QRS complex is ventricular depolarization, and we also know the action potentials in ventricles, right? So if you look at the action potential in the ventricles, the QRS complex indicates ventricular depolarization, okay, and the T wave indicates ventricular repolarization. So QRS complex corresponds to phase 0, ST interval corresponds to phase 2. I repeat, QRS complex, they correspond to phase 0 and 1, but ST segment corresponds to phase 2, T wave corresponds to phase 3, okay, and TP interval for the next wave corresponds to phase 4. Is it clear to all of you? We are integrating the ECG with ventricular depolarization. We are integrating ECG with ventricular depolarization. This is integration of ECG and ventricular excitatory fibers. Okay. Now, one very interesting part, the last part of ECG I would like to mention here. There is something called as cardiac axis and cardiac vectors. How do you find out cardiac axis or cardiac vectors? See, we have 12 leads. Out of these 12 leads, there are 3 bipolar limb leads and 3 unipolar limb leads, right? There are 3 bipolar and 3 unipolar limb leads. Now the direction is very important here. There are 3 interesting points here, 3 important points. Right arm, left arm and left leg, right? Right arm, left leg. Okay. Now when we draw the Einthoven's triangle using bipolar limb leads, when we draw the Einthoven's triangle using bipolar limb leads, we get an Einthoven's triangle in this manner. Yes, and if we just keep the heart here and we start joining all the 3 lines, if we start join 3 lines, see, these are the vectors. Please remember, these are the vectors. This arrow is one vector, this arrow is another vector, and this arrow is another vector. So what we'll be doing is we are going to draw these 3 lines, lead 1, lead 2 and lead 3. We are going to draw these 3 lines but starting from a single point. Now there are 3 different points. We are going to draw them from one single point. Let us try to understand this point, this thing here. Lead 1 is in this direction, so we are going to draw one single point at the center of the heart and we are going to draw an arrow. So we are going to draw an arrow from one single point. This is lead 1. Alright. Now look at the direction of lead 3. So we are going to draw lead 3, same direction. This is our lead 3, same direction. Please try to understand. I am drawing cardiac axis and how to remember them. Cardiac axis. How does each axis is recording? How does each axis is actually pointing towards the heart? And look at the direction of lead 2. So these are the bipolar limb leads. These are the bipolar limb leads. We have just kept the same directions. Lead 1, lead 3 and lead 2. Alright. But just we are drawing from the same point. Is it clear till this point? Is it fine to all of you? Please tell me. I am waiting for your reply. Is it clear to this point to all of you? I am waiting for your reply. Yes, dear students. Yes. Is it clear till this point? Great. Great. That's very nice to hear all of you. Okay. Perfect. Perfect. Now we will go for unipolar limb leads. Now unipolar limb leads means we actually have right arm in place, left arm in place and left leg in place. So we will draw the vectors which are actually pointing toward these 3 points. One pointing toward right arm, one pointing toward left arm and one pointing towards left leg. In this way we have got 6 leads. Please remember we have got 6 leads, 3 bipolar and 3 unipolar. Alright. Yes, Kesari, you are absolutely right. There are 3 bipolar limb leads and 3 unipolar limb leads. And yes, it depends your whole cardiac, means the whole axis of your protector. I can say 180, 0, 360, 60, 90, all those things. If you put a heart on this axis, what will come to know that the apex of the heart lies somewhere between lead 1 and lead 2. The apex of the heart lies somewhere between lead 1 and lead 2, and the impulse in the heart, it travels from SA node to the apex, from SA node towards the apex. So this is the direction of your cardiac axis, and this angle is actually 59 degrees. So cardiac axis is somewhat 59 degrees. Alright, this is how you find out the cardiac axis. Now just pay attention here, one more thing. If suppose there is some extra excitation, I am just mentioning one point here. If there is some extra excitation going in this part of the heart, which is this part? This is the left ventricle, right? This is the right ventricle, this is the left ventricle, this is the right ventricle. So if suppose there is any excitation which is going on onto the left ventricle side, extra excitation means there is ischemic condition. So this extra excitation will pull the axis in that direction. This is called as left axis deviation. If the impulse is pulled towards the lead 1, it will be known as left axis deviation. If there is some extra excitation going into the right ventricle, then this axis will be pulled in this direction. This will be known as right axis deviation. So left axis deviation and right axis deviation is the deviation of the axis from mean axis, which is 59 degree. Okay, so this is the simplest way to remember the cardiac axis and their deviations. Now, how do you label these leads here? How do you label? Because you always have an MCQ on this thing. You can see very clearly that These three leads, lead 3, left AVR, and lead 2. Which three leads? Lead 3, AVL, that is augmented limb lead or left foot. Okay, AVF, sorry, AVF, and lead 2. These three leads, 1, 2, and 3, they are looking at the heart from the base. They are looking at the heart from the base, hence they are called as inferior limb leads. Lead 3, left leg, or you can say the AVF. Yes, Kesar, that's perfect. Going towards plus and minus, plus 60 and plus 120. Yes. So remember, these three leads, they are left axis deviation, and please remember the lead of AVL and lead 1, AVL and lead 1, they look at the heart from the lateral side, so they are called as lateral leads. They are known as lateral leads. Which two leads are lateral leads? The AVL and lead 1, they are known as lateral leads. They are called as lateral leads. And right atrium, the AVR, is known as superior lead. So there are three important locations. Remember, there are three important locations. I will just come to full screen mode here. See, there are, if you look at the heart, we have three leads which are actually looking at the heart from the base, from the lower part of the heart. They are called as inferior leads. Which are the inferior leads? Lead 3, AVF, and lead 2. They are looking at the heart from the very much from the lower part of the heart. Okay. Okay, they are looking at the heart from the lower part. Alright. Inferior leads, lead 3, AVF, and lead 2. They are inferior leads. If you look at the AVL and lead 1, AVL and lead 1, they are looking at heart from the lateral side, so they are called as lateral leads. If you look at the AVR, it is looking at the heart from the topmost part of the heart, so it is called as superior leads. So we have a superior lead, we have a lateral leads, and we have an inferior leads. So you will have to remember this thing: lead 3, AVF, and lead 2. Wherever you have leg in the recording, lead 3 also has left leg in recording, lead 2 also has left leg in recording, and AVF also has left leg in recording. So all the three leads are inferior leads. Lead 3, AVF, lead 2. AVR is looking at the heart from its topmost position, hence called as superior leads. Whereas lead 1 and AVL, they are looking at the heart from the lateral side, hence they are called as lateral leads. So you have to remember this thing: inferior, lateral, and superior. Inferior, lateral, and superior. Okay, these are the three important leads. Actually, we use 12 leads in ECG, and we always use long lead to diagnose the things. Yes, remember there are 12 leads actually: 3 bipolar limb leads, 3 unipolar limb leads, and 6 chest leads. Depending upon the condition where you want to look, where you are expecting the ischemia or anything to occur, any conduction blockage to occur, you specifically look for that lead. If you want to look any conduction blockage in the superior part of the heart, you look for lead AVR. If you want to look any conduction blockage in the basal part of the heart, you will look for these three leads. So depending upon where do you expect the ischemic condition to occur, and on that basis you determine which lead you are going to choose for your diagnosis. Okay, so this is one of the interesting point here. Okay, now let us go to the MCQs here. The false statements about ECG: irregular P waves in atrial flutter, regular QRS complex in complete heart block, high voltage R waves over. Yes. Okay. Kesar has answered very rightly. Everything is perfect. Kesar has studied perfectly. The ECG parts are perfectly done with Kesar. Yes. Okay. So now false statements about ECG: irregular P waves in atrial flutter, regular QRS complex in complete heart block, high voltage R waves over right ventricle in right ventricle hypertrophy, and irregular sawtooth appearance in ventricular fibrillation. See, the three statements are true, only one is false. Oh, sorry, Dharmendra. Yes, you can see 13th question. False statements about electrocardiogram shows irregular P waves in atrial flutter, regular QRS complex in complete heart block, high voltage R waves over the right ventricle in right ventricular hypertrophy, and irregular sawtooth appearance in ventricular fibrillation. Yes, there are three statements that are perfect. This occurs fine. It is always seen. It is also seen in right ventricular hypertrophy, and this is also seen. Yes. So the only option we are left with is, yes, Vivek has answered very right. Irregular P waves. Irregular P waves in atrial flutter. Okay, irregular P waves in atrial flutter. Moving to the next question. Question on cardiac cycle. Isometric relaxation. I'll just bring down the question here. Isometric relaxation. What do you think is the right option? Lasts for only 0.06 seconds. Is a phase during which AV valves open. Is a phase during which pressure inside the ventricle rises slowly. Is a phase during which third heart sound is heard. Which is the true statement? You want to identify the true statement here. True. There are three statements which are false, and you should identify the true statement here. Yes, that's perfect. That's perfect, Mani. Okay. So, what do you think is the 14th question? Isometric relaxation here. It lasts for 0.06 seconds. Is a phase during which AV valves open. Is a phase during which pressure inside the ventricle rises slowly, or is a phase during which the third heart sound is heard. Yes. See, isometric relaxation means, I'll just give a simple hint here. This is the atria, ventricles, and this is the aorta. Now, when ventricles start relaxing, the AV valve is already closed. The aortic valve also closes. Now, in isovolumetric relaxation means both the valves are closed, still ventricles are relaxing. So, this is not a right statement. Is the phase during which AV valve open? No. Oh, everybody answering C. No. See, it's a relaxation. In relaxation, the pressure in the ventricle is going to decrease. The pressure is going to decrease, dear students. The pressure is going to decrease, not increase. You want to find a true statement. So even this is a wrong statement. Third, is a phase during which third heart sound is heard? No heart sounds are heard during these phases. The right answer here is only A. I think I have to discuss. We'll have to discuss cardiac cycle in detail. Shall we go for cardiac cycle discussion? Or do you want to have a pause or sort of? Yes. Do you want to pause here for a while? You want a break of 5-10 minutes? Because we are going to start cardiac cycle, which will take at least 20 minutes. What do you say, students? What I can see is none of you answered this thing right. Right answer is A. Yes, the right answer is A. Isovolumetric relaxation or isometric relaxation is last for 0.06 seconds. Yes, sir means what? Do you want a break of 10 minutes? Do you all want a break of 10 minutes? Yes, students? Definitely B is not correct because AV valve doesn't open. See, isometric means what? Yes, let me clarify the doubts here, Mani. Isometric means no change in volume, no change in size. Since there is no volume change in volume, no change in size means none of the valves is going to open. What they are saying is a phase in which AV valves open. Why? It's an isometric. No valve is supposed to open here. No valve is supposed to open here. Okay. Okay, so I will continue. I will do cardiac cycle and then we will take a break. Okay. Okay. And not a break in a sense, just a 2 minutes break. Okay, just a 2 minutes break so that you just all get fresh. That sort of break. Okay. And I will get my cup of coffee. Okay, no break. That's also fine. That is also fine. Okay, okay. See, let us go with cardiac cycle. Let us start cardiac cycle. Okay. See, in cardiac cycle, remember, why is it going? Okay. See, when you look at a cardiac cycle comprises of atrial systole, atrial diastole, ventricle systole, ventricle systole. The overall cardiac cycle is of 0.8 second. The overall cardiac cycle is of 0.8 seconds. Now, how do we get 0.8 second? The 0.8 second is because you divide 60 seconds by 70 beats of the heart. 60 seconds, because in 1 minute we have 70 to 72 beats. So in 1 beat, how many seconds? Okay, how do you get this point? I will again come to this, explain in simple way. In 60 seconds we have 72 beats. In 60 seconds we have 72 beats. So for 1 beat, how many seconds? So cross multiply, and hence you have 60 into 1 divided by 70. So 60 by 70 gives you 0.8 second. This gives you one very important thing. As the heart rate will increase, the cardiac cycle duration will decrease. So increase in heart rate decreases the duration of cardiac cycle. It means as the heart rate will increase, the cardiac cycle duration will keep on decreasing. Alright. So we will consider a normal 0.8 second cardiac cycle. Now this 0.8 second is for both, means atrial systole, atrial diastole 0.8 second, ventricle systole, ventricle diastole also 0.8 second. Please remember, atrial systole, atrial diastole 0.8 second, okay, and ventricle systole and ventricle diastole also 0.8 second. So overall timing should be 0.8 second, but individual timings may be different. The atrial systole is of how many seconds? 0.1 second. Atrial diastole is of 0.7 second. Ventricle systole is of 0.3 second, and ventricle diastole is of 0.5 second. Please remember, atrial systole is of 0.1 second, atrial diastole is of 0.7 second. Together it makes 0.8 second. Ventricle systole is of 0.3 second, ventricle diastole is of 0.5 second. Together they make 0.8 second. So individual timings may be different, but overall the cardiac cycle gets over within 0.8 second. Okay, means your heart completes its whole event in 0.8 second. Now whenever you study cardiac cycle, remember two rules here. First rule, that the contraction and relaxation is purely time based. Remember, systole and diastole is time dependent. Whereas, please remember, systole and diastole is time dependent, whereas the second rule is opening of the valve. Remember, opening of the valve is pressure dependent. Okay, contraction relaxation of the chambers is purely time dependent. If ventricle systole is of 0.3 second, they will contract for 0.3 second. But the blood which is moving from one chamber to other chamber, from ventricles to the pulmonary artery or aorta, is not time dependent. It is purely dependent upon the pressure difference across two areas. So remember two important things here. Systole and diastole is time dependent, but opening of the valve is pressure dependent. It is just like the pressure cooker. If you keep a pressure cooker on a gas, you know the timing that you have kept it at 1 p.m. in the afternoon, but you will never be able to guess that at what exactly timing you are going to have the whistle. Whistle occurs only because of pressure in the pressure cooker. The whistle is not time dependent. That means at 1 o'clock you will keep the pressure cooker, at 1:05 you are going to have a whistle. That's very rarely to happen. Okay, so the chamber systole and diastole is time dependent, but the opening of the valve and movement of the blood is pressure dependent. Alright, so let us put all the events in this atria and ventricles now. We will draw one ventricles and atria. Okay, draw ventricles and a atria. Okay, and also an aorta. Okay, so we have ventricles, we have atria, and we have aorta. Now there are two valves here, AV valve. One is AV valve and one is aortic valve, right? One is AV valve, one is aortic valve. Now if you see the AV valve and aortic valve, whenever AV valve will open, the blood will move from atria to ventricles. Whenever aortic valve will open, the blood will go from ventricles to the aorta. Alright, now let us go by sequence. Let us say atrial event first. The atria contracts. What is the first event? Is atrial systole, right? And when atria is under systole, the ventricles are under diastole. The ventricles are under diastole. Whenever atria is under systole, see, it's always like this: systole, diastole, systole, diastole. So whenever atria is under systole, the ventricles are under diastole. So atria is under systole, ventricle is under diastole. So atrial pressure is more than ventricular pressure. Atria contracts, atrial pressure will increase, atrial pressure will be more than ventricular pressure, the blood will move from atria to ventricles. Because the pressure of the blood is more onto the other side, this blood will keep the aortic valve always closed. Okay, now since atrial systole is of 0.1 second, the atrial contract for 0.1 second, the blood is moved to the ventricles, atrial systole is over. Now atria is going to go under diastole. Okay, now atria is going to go under diastole. Now ventricle systole starts. Ventricle systole will start, and ventricle systole is of 0.3 second. Ventricle systole is of 0.3 seconds. So there are going to be 3 phases of ventricle systole. 3 phases. Can you tell me what are those 3 phases, dear students? Those who are online, can you tell me what are those 3 phases of ventricle systole? Yes. What are those 3 phases of ventricle systole? What are those 3 phases of ventricle systole? Yes. What are those 3 phases? Ventricle systole is 0.3 second. There are 3 phases. First, isovolumetric contraction. Isovolumetric contraction. Okay. Second, rapid ejection phase. Second, rapid ejection phase. And the third, slow ejection phase. Yes, very good, Urjita. Rapid ejection phase, slow ejection phase. Now, how does it happen? What are the importance of these 3 phases? See, when ventricle starts contracting, because ventricular pressure is more than atrial pressure, the AV valve closes. The closure of AV valve gives you first heart sound. Okay, it gives you S1. So you get S1 because of isovolumetric contraction. Now when ventricles contract isovolumetrically, there is no change in the volume, there is no change in the size, no change in the volume of the blood, no change in the size of the chamber, but there is a tremendous rise in the pressure. The ventricle pressure becomes more than aortic pressure. The ventricle pressure becomes more than aortic pressure. The aortic valves open and the blood moves from the aortic valves open and the blood moves from, yes, the blood moves from ventricles to the aorta. Okay, the aortic valve is open and the blood moves from ventricles to the aorta, called as rapid ejection phase. Now afterwards, the ventricle blood has moved to the aorta, so the blood initially moves very rapidly and then the blood goes slowly. So first there is a rapid ejection phase and then there is a slow ejection phase, because once the blood has moved to the aorta and aortic valve is open, the pressure difference is slightly lesser, but still the ventricular pressure is more than aortic pressure. So blood keeps on moving initially rapidly and then slowly. So this is the contraction. This is the isovolumetric contraction, rapid ejection phase and slow ejection phase. Okay, is there any doubt here? S1 sounds occur in rapid ejection phase. Isovolumetric contraction before rapid ejection phase. Now, when ventricle systole is over, ventricles they go under diastole, and ventricle diastole is of 0.5 seconds. So there are 5 phases. Ventricle diastole is of 0.5 seconds. So there are 5 phases. And what are those 5 phases? Remember those 5 phases. Number one, protodiastole. Then isovolumetric relaxation. Then rapid filling phase. Then slow filling phase. And then last rapid filling phase. So there are 5 phases in ventricular diastole: protodiastole, isovolumetric relaxation, rapid filling phase, slow filling phase and last rapid filling phase. Let us see how does this occur. Now ventricle systole is over, ventricles are going to go under diastole. So see here, now ventricles will go under diastole. Now what happens? See, now when the ventricle starts going under diastole, see, AV valve was closed initially. AV valve was closed, right? The AV valve was closed initially. When ventricle starts relaxing, the blood starts moving from aorta back to ventricles. In protodiastole, ventricles have started relaxing. Yes. First thing is protodiastole. What happens in protodiastole? Try to understand this point. When ventricles start relaxing, they have not relaxed yet. They have started relaxing. But because ventricles started relaxing, the blood from the aorta, it tries to jump back, because there is a huge amount of blood which has come from ventricles to the aorta. This huge blood, it tries to jump back, and this blood flow from aorta towards ventricle, it causes closure of aortic valve. And this causes S2, second heart sound. So closure of AV valve causes first heart sound and closure of aortic valve causes second heart sound. In isovolumetric contraction, ventricle contract, AV valve closes, causing first heart sound. In isovolumetric relaxation, the ventricles start to relax. They are not relaxing yet. The protodiastole gives you second heart sound. Now since aortic valve is closed and AV valve is not yet open and ventricles are relaxing as a closed chamber, this relaxation is called as isovolumetric relaxation, because ventricles are relaxing as a closed chamber. Both the valves are closed, ventricles are relaxing as a closed chamber. Advantage: tremendous drop in a pressure in a very short time. If I would ask you one question here, at the end of isovolumetric relaxation, please answer this question very carefully. At the end of isovolumetric relaxation, when AV valves open, what is the pressure in the ventricles? What is the pressure in the ventricles when AV valves open? Yes, please let me know the number. What is the pressure in the ventricles when AV valves open? At the end of isovolumetric relaxation, what is the pressure in the ventricles? Should I give you the options here? 25, 5, 25, 10, 5, 0. Yes, Mani? Is it 0? Perfect, absolutely right. The pressure in the ventricle is 0 mm of Hg. That's why the AV valves open and the blood goes from atria to ventricles. Okay, so the blood starts filling. This blood which is filling in the first rapid filling phase, it gives you S3. The blood strikes onto the ventricular walls, gives you third heart sound S3. So S1 is because of AV valve closure, S2 because of aortic valve closure, and S3 because of rapid filling phase of the blood, first rapid filling phase. And the moment first rapid filling phase gets over, the pressure, both atria and ventricles have same pressure, so the blood moves slowly, known as slow filling phase, or diastasis. Now after diastasis, the atria starts contracting, because in the last rapid filling phase of the ventricles, the atrial contraction time starts and atria contracts, and the last part of the blood is also pumped in the ventricle, known as last rapid filling phase, and the contraction of the atria causes S4. So S4 is because of atrial systole. It occurs during atrial systole because of last rapid filling phase. So there are, yes, that's perfect. Everybody answered very right. 0. During ventricle relaxation, the phase of pressure in the ventricle is 0. So S1 is because of AV valve, S2 is because of aortic valve, S3 is because of first rapid filling phase, and S4 is because of atrial systole or last rapid filling phase. Now, since we have discussed two things, we also going to discuss two more things, JVP and PV loop. Let us just stay in tune for these two more things. JVP. What is JVP? JVP is jugular venous pulse. JVP is jugular venous pulse. How does it occur? It's a pressure of the atrial changes which you record from the right atrium into the jugular vein. Okay, the right atrial pressure changes which you observe in jugular vein. Now, we observe jugular venous pulse, but we actually interpret the ventricular pressure. Please remember one important point here. You observe jugular venous pulse or jugular venous pressure, but you interpret the ventricular phases. Yes, isovolume relaxation, all the valves are closed. Definitely money. Sure, that's why. At the end of isovolume relaxation, the AV valves open. You got the answer. I think you have the doubt, no? The one who has the doubt about isovolume relaxation. Yes, money. You got it, the question now? At the end of isovolumetric relaxation, the AV valves open and then the blood starts moving. Okay, at the end of isovolumetric relaxation, not before that. Isovolumetric means what? No change in the volume. Isovolume. Okay, tell me yes or no. Okay, so during isovolumetric relaxation, all the valves are closed. After isovolumetric relaxation, when ventricular pressure becomes lesser than atrial pressure, the AV valves open. Okay, now see, let us get onto the JVP. Very interesting way of JVP. In JVP, you record atrial pressure changes. So start with A wave. When atria contracts, the pressure in the atria increases, you record A wave. What do we record? We record A wave. So A wave is because of atrial systole. That's perfect. That is always perfect. It is always right. But atrial systole is of 0.1 second. The moment atrial systole gets over, the ventricle starts contracting, and in ventricle contraction, the AV valve is closed, first heart sound, and ventricle still continue to contract. Because of isovolumetric contraction, the ventricular pressure becomes much more higher than atrial pressure. So it causes bulging of the valve. AV valve into the atria. Because of AV valve bulges into the atria, the pressure in the atria still increases, and we record C wave. Okay, C wave because of increased pressure. Now the moment isovolumetric contraction gets over, the aortic valves open. Not aortic here, it's a pulmonary valve. We are talking about right atrium, so we are talking about pulmonary valve. So pulmonary valves open and the blood from ventricle jumps into the pulmonary artery. and from the left chamber jumps to the aorta, blood goes from ventricles to the aorta. Yes, right atrial pressure, yes. So when atria, but it is taken as a representative for everything in the heart. It's like a phases changes. So when ventricles start contracting, initially because of ventricular contraction, remember the AV valve bulges into the atria and gives you C wave. Now, since the ventricular pressure becomes more than the pressure of the aorta on the left side and right ventricular pressure becomes more than pulmonary artery, the valves open and blood starts moving from ventricles into the respective vessels. Because of this, what happens? The pressure in the ventricle decreases drastically. This causes the valve to jump back easily. Since the valve jumps back to its original state, the pressure decreases. So you have X descent. So X descent indicates what? The ejection of the ventricles. Please try to understand this point. The X descent indicates ejection of the blood from the ventricles. Now the moment ejection of the blood of the ventricle is over, the ventricle start relaxing, and the moment ventricle starts relaxing, what will happen? The valve is again closed. Pulmonary valve is again closed on the right side, aortic valve is closed on the left side. So closure of the valve and ventricles are relaxing, isovolumetrically. Isovolumetric relaxation. Now when there is an isovolumetric relaxation, the valves are closed, both the valves are closed, still ventricles relaxing, and during this phase blood is getting filled in the atria. So this causes increased pressure. Increase in the pressure. You got it as a V wave. So V wave indicates what? V wave indicates isovolumetric relaxation and also filling of the blood in the atria. Okay. Now the moment isovolumetric relaxation gets over, the AV valves open and the blood jumps from atria to ventricles. And this causes atrial pressure to decrease. So you have one more descent, that is Y descent. And after this Y descent, again atria contract and again we have A wave. So in this way you have ACV as an ascent or upstroke, X and Y as a downstroke. Yes, Shabnam. Because atrial pressure is more, that's why the blood is moving from atria to ventricles. Remember. And why it is more? Because ventricles are relaxing, so ventricular pressure is 0 and atria is getting filled with the blood, so atrial pressure keeps on increasing. So atrial pressure somehow becomes more than ventricular pressure because ventricles are relaxing and atria is getting filled with the blood. So the ventricular pressure becomes 0 and blood goes from atria to ventricles. It's a pressure gradient here. Okay, is it clear, Shabnam? Now let us write down the events here. A wave is because of atrial systole, right? A wave is because of atrial systole. C wave is because of, yes, isovolumetric contraction of the ventricles, right? Isovolumetric of the ventricles. X wave is because of rapid ejection phase and slow ejection phase. V wave is due to isovolumetric relaxation, and somewhere before the V wave the aortic valve and IA is greater than that in the aorta and aortic valve is open. Yes, in the right side, in the left side of the heart, the ventricular pressure. Yes. Y wave. What is the Y wave? Y wave is because of the ventricular filling, rapid filling phase and slow filling phase. And again A wave is atrial systole, last rapid filling phase. The last rapid filling phase. I hope these phases are clear to all of you. Is it clear to all of you? I'll just repeat again. A wave is because of atrial systole. The atria contracts, the pressure in the atria increases, you have A wave. Then C wave is because of isovolumetric contraction of the ventricles. The AV valve bulges into the atria. The AV valve, if you want to write, you can write down this point also. AV valve bulges into the atria. Okay. Then X descent is due to what? The AV valve has open, not AV valve. The pulmonary valve has opened and the blood has gone from ventricles to the pulmonary artery. So you have rapid ejection phase and slow ejection phase. Opening of you can say opening of pulmonary artery on this side, and the left side opening of the aortic valve. Pulmonary valve. Opening of the pulmonary valve. Okay. Then why V wave? Because isovolumetric relaxation, and the other cause is increase in atrial pressure due to filling of the blood in atria. Due to filling of blood in atria. Okay. Yes, tell me, Kesar. And Y wave. And what is Y wave? Y wave is due to the blood is now moving from atria to ventricle. Blood is moving from atria to ventricle. So pressure again decreases. So Y descent is rapid filling phase and slow filling phase of the ventricles. Okay, slow filling phase of the ventricles. And also you can say that it is emptying of atria. You can say. And A wave is again last rapid filling phase where atria is contracting. Now I will also indicate two more things here. Which two things I am going to indicate here? I am going to indicate here heart sounds. A wave, which heart sound? A wave, which heart sound? Tell me. Please everybody tell me here. A wave, which heart sound? A wave is which heart sound here? Anybody? Please tell me. A wave is which heart sound? Yes, people in a group. S1, S2, S3, S4. A wave is which heart sound here? Yes. Are you people online? I can see there are few people online. Yes. A wave is which heart sound here? Yes, Mani, Kesar, Shabnam, John, Vishakha, Manish, Dharmendra, Arjita. Students are tired. Very good. Yes, S4. Heart sound 4. Atrial systole gives you S4. Very good. C wave, which heart sound? S1. C wave, S1. X descent, any heart sound? No. V wave, just before V wave you have one more heart sound. At this point you have S2. At somewhere around before isometric relaxation we have S2. And rapid filling phase gives you S3. So you can say that which wave corresponds to which heart sound. A wave corresponds to S4, C wave corresponds to S1. Okay, just before V wave you have S2 and Y wave corresponds to S3. Yes. That's perfect. Yes, perfect. Okay, that's what I wanted to listen to from all of your side. That's yes, you got the point here. We are integrating heart sounds along with JVP. Now we are also going to ECG. We are also going to indicate ECG in JVP. Please remember, we are going to indicate ECG in this JVP now. See, how do you indicate ECG into JVP? A wave is atrial contraction, means atrial excitation, right? So atrial excitation means P wave. So A wave will correspond to P wave. Okay. C wave is ventricular excitation and ventricle starts contracting. So C wave will correspond to QRS complex. C wave will correspond to QRS complex of ECG. Alright. C wave will correspond to QRS complex of ECG. And now ventricles are relaxing. So when ventricles start relaxing, it is at S2. So the S2 corresponds to T wave. S2 corresponds to T wave, and S3 is somewhere between T wave and next P wave, because again you have a P wave. I'll label the things here: P wave, QRS complex, T wave, and again P wave. So P wave S4, S1 QRS complex, T wave S2, and S3 between T wave and P wave. Okay. Yes, okay sir, MCQs are there, many MCQs are there from JVP, heart sounds and ECG. Yes Shabnam, V wave in atrial filling. See, atrial filling, actually in atrial filling, the V wave will show decreased pressure. The V will show decreased pressure. Yes, A wave and P wave. Yes, perfect, you are answering. Shabnam, JV in atrial filling, actually whenever there is okay, V wave in atrial filling, let me check. Yes, V wave in atrial filling, yes, you are right Shabnam. And Shabnam has answered Y wave is due to atrial emptying. Yes, Y wave is due to atrial emptying. Yes, you are right Shabnam. Vivek has answered A wave is P wave. Yes, perfect. Yes, sir. Yes, I can read the responses here. Now one more thing I am going to integrate. The ionic basis of action potential. In P wave it is SI node excitation, so you are going to have pacemaker potential here, whereas QRS complex is ventricular depolation, so we are going to have the Purkinje fibers action potential, and T wave is relaxation. So now again see, this is very interesting here. The QRS complex corresponds to 0, 1, ST corresponds to 2 wave, T corresponds to 3 wave, phase 3, and this S3 sound, they corresponds to phase 4. Okay, so the phase 2 corresponds to ST segment, and S2 sound occur in phase 3 of ventricular action potential. That's how it occurs. Okay, I hope I am not confusing all of you. It's not confusing, it's very simple, it's very interesting. You are integrating JVP with heart sounds, with ECG, with action potentials of the heart. Okay, is it clear to all of you? Yes, dear students, is it clear to all of you? Please reply me. So we are just revising the things. A is atrial contraction, perfect. C is ventricular contraction. Yes. V is venous filling. V is venous filling. Yes, atrial filling. That say you can say. And X is atria relaxing. X, atria is always relaxing. See, from A to Y. Please remember, everyone. From A to Y, it is always relaxing only. Okay. So X is atrium relaxing. Atria is relaxing only. Atria, X is actually blood is moving out from ventricles to the respective things, respective places. And Y is this, Y descent is filling. You can say X wave is ejection of ventricles. Please, okay, so just make a correction. X wave is ejection of the blood from the ventricles. Yes, I can see many students have said yes and yes. Shabnam, any doubts here, Shabnam? Yes, any doubts here? Okay, so yes, thank you Vivek. So everything is clear now. Now let us just solve the MCQs, and then We will take a break. Which of the following statement regarding JVP tracing is false? A wave due to atrial contraction, it's the right statement. AV valve bulges upward during ischemic contraction of the ventricle, causing upstroke of C wave, right statement. V wave occurs due to ventricular filling. V wave occurs due to ventricular filling. No, in V wave ventricular filling does not occur. In V wave ventricular filling does not occur. Downstroke of C wave is caused due to pulling of AV ring downwards when the ventricle starts contracting tonically. Downstroke of C wave is caused due to pulling of AV ring when the ventricle starts contracting isotonically. What do you think is the right answer here between A, B, C and D? Yes, the right answer is C. The V wave occurs during atrial filling, not ventricular filling. Yes, the V wave occurs due to atrial filling, not ventricular filling. Okay. Yes, C statement is the answer. Very right. If EDV is 130 and ESV is 50, then ejection fraction is how much? Very simple. Stroke volume is 130 minus 50. See, 130 is the amount of blood in the ventricles. Yes. 130 minus 50, stroke volume is how much? 80. 80 ml is less than 60%, is less than 80%. So answer is 60%. Okay. Yes. If EDV is 130 and ESV is 50, then ejection fraction 80 ml is how much percentage of 130? 80 ml is how much percent of 180? See, 80 ml, okay, is how much percent of 130? That's what you want to say. So 80 into 100 divided by 130 is the answer, and that's how you find out. So 13 something, 13 6 are 72, 13 7s are 84, 13 6 are something 60. So answer is 60%. That's perfect. That's really perfect. Okay. Going to the next question. Maximum blood flow per 100 gram of tissue. Maximum blood flow per 100 gram of tissue is brain, heart, kidney, liver. Where do you have maximum blood flow? Where do we have maximum blood flow? Yes, students. Where do we have maximum blood flow? Just think. Answer is, for 17 the answer is no, not A. Answer is kidney. The maximum blood flow per 100 gram of tissue is in the kidney. Kidney. The answer is kidney. The maximum blood flow per 100 gram of tissue is always kidney. Okay. Kidney has highest blood flow as compared to anywhere else in our body. Not heart, not brain, not liver. The answer is kidney. Please remember this point. Kidney has highest blood flow. Next question. The percentage of blood that is present in capillaries is, the percentage of the blood that is present in the capillaries is 5%, 10%, 15%, 20%. Yes, please. For 18th question, please answer for 18th question. For 18th question, it is 5%. Remember, the amount of blood in the capillaries is 5% of the total cardiac output. Okay, the percentage of blood that is present in the capillaries is 5%. Okay, it is 5%. The percentage of blood present in the capillary is 5%. All right, 5% of the total blood flow. Yes. Peripheral resistance is inversely proportional to. See, increase in viscosity will increase the resistance. Increase the length of the vessel will increase the resistance. Increase the elasticity will increase the resistance. But decrease in the radius will increase the resistance. So the inversely proportional ratio is going to be answer A. No, John, it is 5%. Capillary blood flow is 5% of the total blood volume. Alright, please remember. And maximum amount of blood is in which vessel? Aorta, capillaries, arteries, arterioles, veins. Yes. If I would like to ask you this point, maximum blood flow is in which part of the circulation? Capillaries, aorta, arteries, or veins? Maximum amount of blood is lying in which part of the circulation? Yes, peripheral resistance is inversely proportional to radius of the vessel. Decrease in the radius increases the resistance. Decrease in the radius increases the resistance, and that's how you can say that it is inversely proportional to the resistance. The rate of lymph flow is lymphatics 10 ml per hour, 20 ml per hour, 50 ml per hour, or 120 ml per hour. No, for that the answer is not aorta. Remember, maximum blood is in, I will write on this point here, maximum blood is in veins. That's why they are called as capacitance vessel. Capacitance vessels means almost 50% of the blood is in the veins of your body at any given point of time. Okay. The rate of lymph flow is for what answer will be C? Let me see. Yes, Shabnam, could you be more specific about your answer? The rate of lymph flow is yes 120. That's right. That's absolutely right. The rate of lymph flow is 120 ml per hour. The rate of lymph flow is 120 ml per hour. Yes, that's absolutely right. So this is all about CVS. We will discuss RS after a break of 5 minutes. Okay, I'll just take a break of 5 minutes. Almost 50%. Yes, almost 50% is in your venous circulation. Remember this point. Maximum blood flow is in venous circulation. Yes. No, Vikram, it is 120 ml per hour. Yes. Shall we take a break of 5 minutes? Yes, students. Just a 5 minutes break for every one of us. Okay, I'll just take a pause here. So, hello students. Yes, let us start again. I hope everybody has joined. Yes, friends, I have just started the session, so let me see how many of us are. Yes. Hello, Arjita. Arjita has joined back again. Yes, great to see you all back. Nice to see you all. And okay, wait. Manish has asked me to wait. Why, Manish? Okay, we'll wait for a while. So, yes, I can see 19 students have joined so far. We have a pretty good number of students joining us. Okay, so we'll go with the yes, because post lunch break or post tea break, some students might. Okay, how many of you are from our FMG students? May I just have a yes from the FMG students? Yes, Ankit, we will start definitely. You just wait for 2 more minutes. Just 2 more minutes. I want to have a yes from FMG students or a thumbs up from FMG students. I don't know, Shabnam. I do get this comment, or you can say compliment. I'm always like this. I don't know. It's something which is my inherent nature. I always I'm always smiling. Okay. Okay. Great. Great. Okay, we have students come joining us. Yeah, please spread the word among your WhatsApp group or your child group that session has started. Just a request. So that meanwhile, when we will start our teaching, so that many more students will join us. Okay, just spread the word that the session is again started, and we are starting with the respiratory system. Okay, so we'll solve the MCQs first, all the MCQs, and then we will try to understand few of the concepts in the RS. Natural. Okay. Yes, nice. Okay, so let me first give some introduction part here. Okay, some introduction part. Let me give some introduction part here. See, the respiratory system, it includes 4 major chapters in it, or you can say you can study respiratory system under 4 main categories, starting from mechanics of breathing, then transport of gases, then regulation of respiration, and then the applied physiology, that is hypoxia and high altitude and deep sea diving physiology. These are the 4 major categories under which we'll be studying the respiratory system. Always remember, you do have questions from respiratory system, and it includes much of the concepts in the physics which are very much applied onto the physiology. The respiratory system includes too much of physics, like gas laws, diffusion, coefficient, size, and many more, like pressure gradient. Many other things are actually included in the study of respiratory system. Much more physics is involved. Keeping that in mind, we'll try to understand few physics concepts also. So first question, conducting zone. Yes, Mani. Yes, Mani, what's your question? Yes. Are you all in how much pressure in aorta in veins? Okay, that's an interesting question. let me help you with the diagram here. The pressure in aorta, depends upon the pressure in the ventricles. Now see, shift. Yes. See, when you talk about the pressure gradients here, the pressure in the aorta when the valve is closed, and when the blood is pushing on this aortic valve, do you know with what pressure the blood is pushing back on aortic valve? With what pressure the blood is pushing back on the aortic valve? The back pressure is a pressure of peripheral resistance, and this pressure of peripheral resistance is actually 80 mm of Hg. So the aortic valve is closed with the pressure of 80 mm of Hg, and when the ventricles contract, the moment ventricular pressure becomes 81, the valve is open, and ventricles still continue to contract, and the pressure reaches to 120. So the 120 pressure which is causing the blood to move is not a pressure of aorta, it is a pressure of ventricles. Okay, the pressure with which the blood is moving from ventricles to aorta is 120 mm of Hg, and the pressure with which the blood is pushed back to the aortic valve is 80 mm of Hg. Now this pressure with 120, it keeps the blood moving ahead and ahead, and at every point from aorta to arteries, arteries to arterioles, arterioles to capillaries, and capillaries to venues, and venues to back to veins. Alright, so the pressure, remember, the pressure at the head of vena cava is 0. Yes, the pressure at the head of vena cava is 0. So pressure over 120 keeps on decreasing from 120 to arteries still have 120, not more and more less, but at arteriole the pressure drops down to, at arterial pressure the pressure drops down to 60, and at veins it is 40. So the overall pressure keeps on decreasing from 120 to 60, and it keeps on decreasing at every point, and at the venous end it is 40, and it keeps on decreasing and becomes 0 finally when it reaches to the right atrium. So the pressure keeps on decreasing right from aorta till the veins. Okay, is this what you wanted to know, Mani? Or else you would like to understand one more point, the important point is PV loop that I have not covered in the previous session. So let us cover a point on PV loop, pressure volume loop. Okay, see, a pressure volume loop comprises of volume change on the x-axis and pressure changes on y-axis. Now we are talking about a pressure volume loop, PV loop of left ventricle. So let us start with a very simple point. No, Rajesh, when you measure blood pressure, you record blood pressure by arterial pressure 120 by 80. 120 is systolic pressure, which is the pressure of the ventricle, and 80 is the diastolic pressure, which is the pressure of peripheral resistance. So diastolic pressure is the pressure of peripheral resistance, not ventricular pressure, because when ventricles are relaxing, the aortic valve is closed. When ventricles are relaxing, the aortic valve is closed, and when aortic valve is closed, please remember, the 80 mm of Hg pressure will not represent it here, because during relaxation the ventricular pressure is 0. So this is 0 and this is 80. How? Because of the aortic valve which is closed, because there are two chambers here. No, blood amount is very high. See, please try to understand, there are two chambers. When the aortic valve is closed, the overall circulation is divided in two chambers. One chamber is left ventricle and one chamber is blood circulation, or the arteries and arterioles and veins and arteries and aorta. These two chambers are separated by the aortic valve, and this follows one law, and that law is known as Pascal's law. Pascal's law says that the pressure in a closed chamber is always exerted equally on all sides. On sides the pressure is always same because it is closed, so the pressure of 80 will not be represented here, and because it is closed, the 0 will not be represented here. Okay. Okay. Is it clear, Mani and Rajesh? Okay, sir, pulse pressure is different from venous pressure. Please remember, pulse pressure is the pressure by which the blood is flowing in the arteries, in the arteries, and that's a different thing. Okay. So let us go to the MCQs of respiratory system. Conducting zone of airways. Conducting zone of airway extends from nose to respiratory bronchioles, nose to terminal bronchioles, nose to bronchi, nose to alveolar ducts. What do you think is the answer? Conducting zone of airway extends from nose to respiratory bronchiole, nose to terminal bronchiole, nose to bronchi, nose to alveolar ducts. See, lungs is divided almost how many times? Lungs is divided almost from trachea to bronchi to bronchioles. Lungs is divided almost 23 times. From 0 till further divisions, the lungs is divided almost 23 times. So at 23rd division you have alveoli. Remember, at 23rd division you have alveoli. So the answer is yes, from nose to terminal bronchiole is the conducting zone of the airway. It is still 16th division. The terminal bronchiole is still 16th division. Remember, and from 17th division onwards, yes, what do we start? We start with respiratory bronchiole. Okay. Now I would like to ask one more point here, one question here. What is the distance from 17th to 23rd division? What is the distance between 17th to 23rd division? Is it 50 millimeters? Is it 20 millimeters, 10 millimeters, or 5 millimeters? What is the distance between 17th division to 23rd division? What is the distance between 17th to 23rd division? Yes, Vishal. 22nd division is a place where alveoli starts. So at the best number, you always go for 23rd. Even the most terminal alveoli is at 23rd division. It's like a tree. Some branchings, some leaves they occur at 22nd division. Some leaves may occur at 23rd division. Okay. Yes. So from 17th to 23rd division, what is the distance? That's what I wanted to know. From 17th to 23rd division, what do you think will be the answer? Yes, the answer is from 17th to 23rd division. Mani has got a very nice emoji. The answer is 5 millimeters. The answer is 5 millimeters because the diffusion of gas is occurring, and remember, one point at which the diffusion is decreasing is the distance. If the diffusion distance increases, then the rate of diffusion decreases. So we want all the gas to move very better way. So minimum distance is the best way. So 5 millimeter is the distance from 17th to 23rd division. All right, 17th to 23rd we have a okay. Now this nose to terminal bronchiole also accounts for dead space. I will ask one question again. A person whose body weight is 200 pounds. What is the amount of dead space? Is it 200? Is it 150? Is it 100 or is it 250? What do you think the amount of dead space in a person whose body weight is 200 pounds? What is the body weight? What is the dead space in a person whose body weight is 200 pounds? Yes. Kesar, Shefali, Ajita, Dinesh, Ankit, Shabnam. The online class is good, but yes, we have a quite good entertainment when we have face-to-face classes. But right now we have some limitations. But it's okay. We are learning. In a bargain, we are learning something, and that's always a good thing. Yes. Okay. Please, I want few more answers. Everybody start answering this question. Yes. Body weight 200 pounds. The dead space is 150 or 200. Vishaka has answered 100. The answer is actually 200. 1 pound of body weight. Remember, the relation is 1 pound of body weight equals to 1 ml of dead space. How do we get this number? See, first, why do we have 150 as a normal dead space? Why do we have 150 as a normal dead space? See, we consider 70 kg healthy adult male, 70 kg healthy adult male as a normal person, and 70 kg actually corresponds to 150 pounds because 1 kg is 2 pounds, 2.2 pounds. So 70 kg is almost 150 pounds, and that's why it corresponds to 150 ml. Okay, please remember 1 pound of body weight equals to 1 ml of dead space. Apart from this, there is one more formula for dead space, and we will just try to understand that formula because it is very important as far as your exams are concerned. So we'll just get into that formula. See, dead space formula is tidal volume into PaCO2 minus PeCO2 divided by PaCO2 is the formula for dead space. Why? See, tidal volume is 500. And what is the carbon dioxide pressure of carbon dioxide in arterial blood? Can anybody tell me what is the pressure of carbon dioxide in arterial blood? The arterial blood CO2 pressure. Yes. What is the pressure of carbon dioxide in arterial blood? Yes. What is the pressure of carbon dioxide in arterial blood, dear student? Yes, 40. Very good. 40 mm of Hg. So 500 into 40 mm of Hg. Now actually this PaCO2 for arterial blood, it is actually same as that of alveolar air. So alveolar air and arterial blood we consider as same PaCO2. So 40 and 40. Hence we take CO2 as 40. So PaCO2 minus PeCO2. PeCO2 is partial pressure of expired carbon dioxide. See, we have two things: carbon dioxide in alveoli and carbon dioxide we expire. Now whatever CO2 we expire, it is actually diluted in the dead space. Please try to understand one point here. CO2 is produced in your alveoli because of exchange. Whatever CO2 we exhale out, it is getting mixed with the volume of the amount of air in the dead space. So that CO2 is getting mixed with the dead space, it is getting diluted. So the amount of CO2 to the amount of CO2 getting diluted will give the idea about how much is the dead space volume. Okay, so 500 into 40 minus 28, the expired carbon dioxide is 28 mm of Hg, and again 40, which is PaCO2. So the answer is 500 into 40 minus 28. It gives you 12 divided by 40. Okay, so 0 and 0 cancel, and 4 3s are 12. Okay, 4 3s are 12. So 5 into 3 is 15. Oh, one more 0 is there, sorry, and that is 150 ml of dead space. So that's how you get 150 ml of dead space. This is clear to all of you. 500 ml into 12 upon 40, and that's how you get 150 ml of dead space. Now, very interestingly, once you become once you go in post internship and once you join any hospital, remember, if you are given a position, or if you are posted in an anesthesia department, then it becomes very important to know the dead space of a person, because unless until you don't know the dead space, you will never be able to understand or calculate the amount of anesthetic drug to be given to the person by inhalation. Because more the dead space, more the amount of drug will be required. Lesser the dead space, lesser the amount of drug will be required. So this formula is very important for all the anesthetic department in all the anesthesia. Okay, so this is one very interesting point here for the dead space. Let us go to the next question here. Following are the functions of conducting zone, except it is a low resistance pathway for air. It defends against microbes and other toxic agents. It warms and moistens the air. It partly does the function of gaseous exchange. Conducting zone and gaseous exchange. Yes, can you tell me the answer for the second question? What do you think is the answer for the second exchange? Same. Yes, sir. CO2, see, in atmosphere there is no carbon dioxide. Please remember, sir. And this formula is working at sea level only. Yes, the answer is D. Everybody's answered it very right. See, sir, your question is for carbon dioxide, and at sea level or at sky level or at high altitude, the carbon dioxide level does not change, because we consider carbon dioxide as almost negligible in the atmospheric air. So CO2 of arterial blood at sea level or CO2 at certain high level will be always remaining same, although it may decrease if we go for hyperventilation at high altitude, but that's a different story. Though arterial blood PCO2 is not dependent on the CO2 of atmosphere. Okay, remember this point, sir. Arterial blood carbon dioxide is not dependent upon the CO2 of atmospheric air. It depends upon what is your how much you are hyperventilating, rate and depth of ventilation, and how much your metabolism in the body is going on. That this thing determine the carbon dioxide of your arterial blood. All right. Okay. Next point. That's perfect. That's very true. Number 3. Major area of resistance during breathing is located in. Now this question is very typical about work of breathing. See, there is a particular decrease in diameter at every point. So what happens? There is going to be a decrease in diameter and increase in the resistance of the airways. So they are asking at which zone, at the initial zone, intermediate zone, or in the last zone, at the alveolar zone. In which zone do you think we are going to have maximum resistance, major area of resistance? Pharynx, trachea, intermediate size bronchi, or bronchioles less than 2 mm diameter? What do you think is the answer? Where do you have maximum resistance? Where do we have maximum resistance? Do we have maximum resistance in the pharyngeal or tracheal area, in the intermediate size bronchi, or in the bronchiole less than 2 mm diameter? What do you think is the answer for this question? Answer question number 3. Yes. Sorry, actually the answer is intermediate size bronchi. Since I can see everybody answers D as option, intermediate size bronchi. Remember, maximum resistance to the airway is in intermediate size bronchi. The last bronchi is cannot be the answer, because at the last or the terminal zone, what happens? The surface area is very high. See, there are two areas where there is no resistance. The initial part, because the diameter is very huge, and the terminal part, the surface area is very high. The intermediate zone is the area where surface area is also very less and diameter is also very less. So at that point, the resistance is very high. Remember this point. Now if I ask you, out of these 4, if I add one more point, that is E, and that is nose, and if I ask you maximum resistance will occur in which of these 5? Maximum resistance. Surface, yes Rajesh Kumar, the intermediate size bronchi is a place where surface area is also very less, and also the diameter is also very less. Whereas at either places, primary or last zone, in the trachea and pharynx, the diameter is very huge, surface area may be less, so no resistance. And in the terminal areas, in the end portions, the diameter may be less but surface area is very high. So both the cases, the resistance will be less. Okay, now answer me this question. Maximum resistance, maximum airway resistance. If the question is, so you have got one option, 1 and 2. Can you tell me which one will you choose? Among maximum airway resistance, which one will you choose? 1 or 2? Maximum airway resistance, what will be your answer? Remember, in maximum airway resistance, the answer will be yes. Okay, I'm getting mixed option. I'll give you a hint and then you can get the answer. Snoring occurs at the nasal cavity, or whenever there is a common cold, whenever there is a nasal blockage, you find it very difficult to breathe. The answer is nose. 50% of resistance, of overall resistance, is in the nose. The maximum resistance is in the nasal area. Please remember this point. Maximum resistance is in the nasal area. Nose is the area where there is a maximum airway resistance. Okay. Next point. Airway resistance can be reduced by administering a beta adrenergic blocking drug, performing maximum forced expiration, increasing vagal impulse to the lungs, increasing lung volumes. What do you think is the answer for the fourth question? What do you think is the answer for the fourth question? Shefali, the nose is not because of hair and mucus here. The nose is because the entry point, the atmospheric air is very large surface area, and the nasal cavity is very small. So this much area air is entering into a very small opening. So this difference in the diameter of large diameter to small opening causes maximum resistance. Whereas from nose to every point this is small and smaller, but from atmospheric air to nose, since the size of the surrounding atmosphere and the nasal cavity very small, so maximum resistance occurs at this point. This is the reason here. Airway resistance can be reduced by, yes, the answer is D, by increasing the lung volumes. Rest at every point it is increasing. So airway resistance is yes, can be reduced by increasing the lung volumes. Rest all the points it is yes, increasing. Means a beta blocker drug will increase the airway resistance because they cause the vasodilation and also constriction of the bronchioles. Maximum force expiration, what happens, how does it increases? See, if this is the bronchi and bronchioles, okay, and this is the alveoli, and when you try to breathe out forceful expiration, when you go for expiration, you are applying a external pressure. This external pressure, if it is very huge, it is very high, then it causes the airways to collapse. If the airways collapse, what will happen? The air will not move out, and this means this will increase the resistance. So forceful expiration increases the resistance by decreasing the diameter of the airways. Vagal impulse, again it will cause constriction in the or decrease in the diameter of vessels and airways, and again it will increase the resistance. But when you go for inspiration, maximum inspiration, we actually causes overall increase in the size of the airways, and that causes decrease in the resistance. Okay, decrease in the resistance. Yes, very good. So smooth muscles is like a sphincter in the following areas: trachea, bronchi, terminal bronchioles, respiratory bronchioles. Yes, smooth muscle is like a sphincter in the following areas. What do you think is the answer for this one? Sphincter, they act like a sphincter, means they can change the resistance of the airways. Trachea, bronchi, terminal bronchioles, respiratory bronchioles. Yes, Mani has answered it 7. See, Mani is 7. Why Mani is 7? 7 is your birth date, Mani. All of you are in Delhi, or you are dispersed? Have you gone to your places? Yes, students. All of you are still in Delhi, or you have dispersed to your respective places? Yes, the right answer is C. Very right. The right answer is absolutely right. C is the right answer. C is the right answer here. Alright. Terminal bronchioles is a place where the smooth muscles, they act like a sphincter. Smooth muscles, they act like. Okay. That's why number 7. Okay. Okay, that's great. Okay. Let us go to the next point. All is true about lungs except it converts angiotensin 1 to angiotensin 2. It partially or totally inactivates many vasoactive substances. It secretes IgA. Resistance in pulmonary circulation is 1 PRU unit. Okay. Okay, Virat Kohli. Virat Kohli. Anushka Sharma. Okay. So what is the answer for 6th one? One thing is false. This is a right statement. Even this is also right statement. This is also right statement. The answer is resistance in pulmonary circulation is 1 PRU unit. Actually, resistance in pulmonary circulation is more than 1 PRU unit. It is almost 5 PRU units, 2.5 to 5 PRU units. Okay, it is more than 1 PRU unit. It is more than 1 PRU unit. Okay. During inspiration, as the diaphragm contracts, the pressure in the intrapleural space becomes equal to 0, more positive, more negative, equal to pressure in alveoli. Yes, Mani. PRU is it's a mnemonic for peripheral resistance of the blood in the vessels. So PRU is peripheral resistance unit. 1 PRU is actually something between the length and the diameter. So the pulmonary circulation is through very small bronchioles, and the the vessels, and that causes that is the reason the resistance is quite more than 1 PR unit. It is more than 1 PR unit. Like it is in the periphery, in the blood circulation, the veins are superficial, so they have a lesser pressure resistance unit, but for the alveolar blood flow it is quite high, more than 1 PR unit. Okay. During inspiration, as the diaphragm contracts, the pressure in the intrapleural space becomes more negative. Let us try to understand with very simple diagram here. See, we have two types of pressure. One pressure is intrapulmonary pressure. In the intrapulmonary pressure, what happens? The pressure in the lungs becomes less when the air moves in, and the pressure in the lungs becomes more when the air moves out. So we take 0 mm of Hg as the relative pressure. It is actually 760. So when you go for inspiration, the pressure becomes 0 to -1, and again from -1 to +1, again from +1 to -1, and again -1 to +1. In this way, the pressure in the pulmonary lungs, pulmonary part, it changes from -1 to +1. So overall pressure change is 2 mm of Hg. How much? 2 mm of Hg is the overall pressure changes. But there is one more area which is just outside the lungs, which is called as pleural space. So in the pleural space, the pressure between the lungs and the pleura this green color is the pleural pressure. So pleural pressure is always negative, even at rest, when the lungs are at 0 mm of Hg. 0 mm of Hg is the pressure when the lungs has done the expiration, but inspiration not started. So the pressure in the lungs and outside lungs is same. When you go for inspiration, the pressure in the lungs decreases, so air goes in. When you go for expiration, the pressure in the lung increases and the air goes out. So it goes from -1 and then -1 to +1, -1, +1. So this is the pressure in the lungs. But in the pleural space between the lungs and the pleura, the pressure even at rest is -2 mm of Hg. So when the lungs go for inspiration, it becomes more negative, and then less negative, then more negative, then less negative. So this pressure is intrapleural pressure. This pressure is intrapulmonary pressure, and the overall difference is known as what? Yes, can you tell me what is this difference known as? The difference between intrapleural and intrapulmonary pressure, what do you call it as? That is the 8th question actually. Which of the following statement is true regarding transpulmonary pressure? The answer is, this pressure is known as transthoracic pressure or transpulmonary pressure. The 8th question is the answer for the first one. Yes, it is equal to intrapleural pressure minus atmospheric pressure. No. It is equal to intrapleural pressure minus alveolar pressure. No. It is equal to alveolar pressure minus intrapleural pressure. This is the answer. Remember this point. Transpulmonary pressure is alveolar pressure or pulmonary pressure minus intrapleural pressure. Okay. Yes. So it is transpulmonary pressure. Okay, it is transpulmonary pressure. Okay. Moving to the 9th question. Bucket handle movement of the ribs. Very simple question. Bucket handle movement of the ribs increases transverse diameter, vertical. See, there are 3 diameters in the lungs during inspiration: the lateral, vertical, and anterior posterior. Yes, a bucket handle movement of the ribs increases which type of diameter? Transverse, vertical, anterior posterior. For ninth question, what do you think is the answer? Yes, please answer this question. It is not all of the above actually. Bucket handle movement. Remember, there are three movements and three diameters in the lungs. There are three movements and three diameters in the lungs. When we talk about ribs, the ribs, they move from more downward position to more upward position. When they move to the upward position, the answer is A, transverse diameter. Please try to understand three important movements of the lungs in mechanics of breathing. Please look here for 1 minute. Okay, everybody. See, in the lungs there are three diameters which can be increased. The lateral diameter called as transverse diameter, anterior posterior diameter, and vertical diameter. When you go for inspiration, all the three diameter increases, but the cause of three diameter increase is different. The lateral diameter, that is transverse diameter, it increases because of the ribs. So the ribs, they move from quite lateral position to downward position to the lateral position by the external intercostal muscles. The external intercostal muscles, they move the ribs in outward direction. Like you hold a bucket and you lift a bucket like this. When you lift a bucket like this, what will happen? The bucket handle movement will increase the lateral diameter. So lateral diameter will be increased. Whereas anterior posterior diameter will increase because of the sternum. Now sternum is connected to the sternocleidomastoid muscles. So when there is an inspiration, this muscle contracts and it pulls the sternum upwards. Now sternum being attached to the ribs, the sternum doesn't move straight way. The sternum moves quite forward and upward. So sternum moves forward and upward. So in this way, the sternum moves upward and forward, called as pump handle movement. Hand pump handle movement of the hand pump is got a sternum movement. Or as a very common example I can say, in movies, Bollywood or Hollywood movies, certain item songs are there, and there the dancers, they show this type of movement. So this is pump handle movement of the sternum, which is very much visible for the female sternum because of the bony structure, and less common in the male pattern of breathing. So pump handle movement of the sternum, bucket handle movement of the ribs, pump handle movement of the sternum, and diaphragmatic movements. These three movements, they cause increase in the overall volume of the chest. As the volume increases, the pressure decreases and the air goes in. Okay, remember this point. All right. I know it's a very funny example, but that is the only example which will always remember, or anybody will always remember. Okay, so coming to the next point. Next MCQ. Yes. Sorry. Okay. Now, could you answer this question? Tidal respiration is caused by. Tidal respiration is caused by contraction and relaxation of diaphragm and internal intercostal muscles. Contraction and relaxation of diaphragm And external intercostal muscles, contraction of abdominal muscles, none of the above. Tidal breathing means normal quiet respiration. Very simple but quite tricky. Very interesting fact here. Tidal respiration is caused by yes, Shefali has started answering. Okay, integrated learning. Yes, I can integrate physiology to any point. Means even to I can integrate physiology to girls shopping. I can integrate physiology to boys shopping. I can integrate physiology to even bathing and brushing. You know, physiology is everywhere. The right answer is B. The right answer for this thing is B, because only inspiration is an active process during normal breathing, expiration is a passive process. So it is causing inspiration and that is active process, where this is expiration in a expiration. But expiration is not active in normal quiet breathing, is not active, is not working. Remember, in normal quiet breathing, the expiration is not active, means the expiration is passive. See, try to understand this point. When we breathe in normally, we just only work for inspiration. So the air is taken in by actively contracting external intercostal muscles. But for expiration, you don't have to work anything. You have to just relax the muscle. The lungs will recoil on their own and the air is given out. So expiration is passive, not active means passive. Okay. B. Answer is B, Shabnam. Because inspiration requires efforts during normal quiet breathing. Tidal means what? Normal breathing. Under normal breathing, only inspiration is worked upon, not expiration. Under normal breathing, only inspiration requires effort, expiration requires no effort. Example, when you go in a birthday and you inflate a balloon, it requires effort to inflate the balloon, but you have to remove the air, just leave the balloon, air will come out automatically. So for expiration, you don't have to take any efforts. So tidal respiration is caused by contraction and relaxation of diaphragm and external intercostal muscles, not the internal intercostal muscles. They will only work when you have a voluntary breathing. Voluntary breathing, like voluntary breathing will only involve external and internal intercostal muscles, both of them. All right. Okay. Let us go to the next question. I hope we are going fine. Everyone is fine till this point. Yes, everyone is fine till this point. I would also request you, please subscribe to the channel, and you can drop down the questions or topic which you want to learn again, so that we will take continuous session, or meanwhile in a break, or as the life continues, so that small topics can be covered in any point of the year. Okay, please remember, because since we are taking this is a marathon class, so I may not be able to cover every topic. Physiology is so vast, it will need at least 60 hours, frankly speaking, to go around say every topic in detail. I will need at least 60 hours. So 60 hours covering in this marathon lecture won't be forcefully. No, not forcefully. In a sense, you can request on a message, or if you want to learn, sir, please explain this topic, say PV loop, or please, sir, explain the refractive error of the eye, or the principle of accommodation. Then we can have these type of things. Okay. So only that is the only thing, Rajesh. It's not necessary, of course. Not necessary. Just in a case you will have someone okay. The slope of pressure volume curve represents what? Pressure volume curve. Conductance, compliance, resistance, all of the above. The slope of pressure volume curve represents what? Conductance, compliance. See, there is something called as delta V upon delta P, and there is a curve here. This is called as compliance. Compliance is a measure of expansibility of an expandable tissue. When you go for inspiration, you expand the chest. Okay, so there is a pressure and there is a volume increasing. So delta V upon delta P is called as compliance. Now, see, listen to me, very interesting. I have got a very interesting example to explain you the compliance. Okay, very interesting example to explain you the compliance. Let us consider compliance with an example here. Take two types of things. One, a birthday balloon, and one, an hot water bag. It is two things. One, a birthday balloon, and other one, a hot water bag. Let us do two type of things here. A birthday balloon and a hot water bag. Now, if you want to inflate a birthday balloon, you just change the pressure a little bit, like, and the volume will increase so much. With small change in the pressure, volume increases too much. So delta V will be too much. Delta P is very less. For birthday balloon, small change in pressure, very high change in volume. So compliance for birthday balloon is very high. Small pressure, large change in volume is high compliance. But on the same time, suppose if you try to inflate a hot water bag which is used for hot fermentation, you keep on applying pressure, it won't inflate. So pressure will be very high, volume will be very less. So to inflate a birthday balloon, less pressure, large volume, good compliance. To inflate a hot water bag, large pressure, small volume, compliance is very low. So your lungs has a specific type of compliance in which with slight change in a pressure, there is a slight change in a volume. And how much is that? Let us write that down point. That is, the compliance of the lungs is 220 ml of expansion with delta V with every 1 centimeter of water pressure. The lungs is 220 ml of expansion with every 1 centimeter of water pressure. This is the compliance of the lungs. Alright. Now remember, there are a few things about compliance which I want you to know. After finishing the 2-3 MCQs, we will go for some important type of MCQs in the compliance. Alright. Now first answer this question also, because all these things are related to compliance. Recoil tendency of the lungs is due to stretched elastic tissue of the lungs, positive intra-alveolar pressure, negative intrapleural pressure, all of the above. What do you think is the answer? Recoil tendency of the lungs. Yes. The lungs, they try to recoil because of what? Is it because of positive intra-alveolar pressure, negative intrapleural pressure? Are you all sure? D. See, negative intrapleural pressure will keep the lung inflated. It will oppose the recoil tendency. Remember, lungs has a recoil tendency, but the negative intrapleural pressure, it opposes the recoil tendency of the lungs. Means we have a lungs tissue, okay, and the lungs, they try to recoil and the chest wants to move out. Because of this opposing tendency, we have a negative intrapleural pressure. Yes, the answer is A. Stretched elastic tissue of the lungs. The elastic tissue is stretched and that causes recoil tendency. Take an example here. When you buy a rubber band, the stretching of the rubber band causes the rubber band to recoil. Okay, it's not you keep the rubber band and it will just recoil on its own. When the lungs are inflated, Okay, that causes stretching of the tissues, and stretching causes its recoil tendency. If we keep a intra-alveolar pressure positive, then what will keep? It will oppose the recoil. Which example? Please remember this B point, yes sir. Specific about Valsalva maneuver. Valsalva maneuver is what? Valsalva maneuver is when you try to breathe out forcefully, keeping the glottis closed. Means you keep the nose closed and you try to breathe out forcefully. This is called as Valsalva maneuver. Please try to understand this point here. How do you differentiate between the pressure of the lungs and yes, see, try to understand. There are two types of maneuver. One is the Valsalva maneuver, and the other one is Müller's maneuver. In both the maneuvers, in Valsalva maneuver, you make the intra-alveolar pressure positive, intrapleural pressure positive in Valsalva maneuver, and in Müller's maneuver, you make the intrapleural pressure negative. How is that possible? It's a very interesting thing. If we try to breathe out forcefully, keeping the epiglottis closed, like you do during defecation, person does during defecation, lifting heavy weight, or a pregnant woman does during parturition, or during constipation, or during urination. Means you take a deep inspiration and you try to breathe out forcefully, keeping the epiglottis closed, so the pressure in the lungs increases. Okay, this is closed. Now if you try to breathe out forcefully, you are getting a pressure, but air is not going to move out. So air is not going to move out, the air is trapped inside the lungs. Once air is trapped inside the lungs, what will happen? The chest and the lungs will come near to each other, and the diaphragm will be moved down. So internal pressure will increase and the content will be thrown out. Whereas opposite is Müller's maneuver. Somebody holds your head and put it into water. You can't breathe, because once you breathe, the water will enter. So you fight for air, but you don't want to breathe from the water. So there is stretching of the chest without stretching the lungs, because you are keeping the epiglottis closed. So it will cause the pleural and parietal membrane, visceral and parietal membrane to separate from each other, and that will cause negative pressure. So we have a negative intrapleural pressure, we have a positive intrapleural pressure. So in Valsalva maneuver, the intrapleural pressure becomes positive. In Müller's maneuver, the intrapleural pressure becomes negative. Simple way. Alright. Let us go to the next question. Surfactant. Which of the statement is true regarding surfactant? Surfactant reduces energy required for respiration. Surfactant decreases surface tension at fluid air interface in alveoli. Prevents pulmonary edema. All of the above. What do you think is the right statement here? Surfactant reduces energy for respiration. Decrease surface tension of the fluid. Yes. Prevents pulmonary edema. Yes. So the answer is going to be, what do you think is the answer here? Surfactant, what do they do actually? Surfactant will actually yes, they will do all the three things. They will do all the three things. The answer is D. The answer is D. They reduces the energy required for respiration, they decrease the surface tension of the fluid, and they prevent pulmonary edema. All three are true. Okay, all three are true here. Okay, all three are true. Yes, absolutely right. Absolutely right. Collapse pressure of the alveoli. Yes, let's go to the 14th question, because everybody answered it right almost. Collapse pressure of the alveoli decreases when radius decreases. sorry, is inversely proportional to surface tension, is inversely proportional to alveolar radius, none of the above. For this you need to understand one law, and it is called as Laplace's law. Laplace's law says that pressure in any alveoli is proportional to 2 times the tension and inversely proportional to the radius. So pressure of the alveoli decreases, the radius decreases, is inversely proportional to surface tension, is inversely proportional to alveolar radius, or none of the above. You can see pressure is directly proportional to surface tension, so no. Decreases when radius decreases, no. Is inversely proportional to radius as well as more the radius, lesser the pressure. Answer is C. For the 14th one, the answer is C. I am just waiting for your reply. Yes. For the 14th question, what do you think is the answer? Yes, Vivek is right. Kashmira, Arjita, Kesar. Kesar, 14th answer is C, not B. It is not inversely proportional to surface tension. It is directly proportional to surface tension. No, not D again. It is C. Yes, Renu is right. Great. Okay. Okay. I hope you know the Laplace's law. And now, since we have done surfactant and since we have done compliance, let us try to have one idea. See, let us please remember this relation what I am writing here. Increase in surfactant increase in surfactant increases the inflatability of the alveoli, increases the surfactant, increase in surfactant increases the inflatability, decreases the collapsibility, increases the compliance here, and decreases work of breathing. Remember this relation here. What is work of breathing? When you breathe, there is an amount of work you done. So if there is a less surfactant, you will need too much of work to inflate alveoli. But if surfactants are more, we don't need much work to inflate the alveoli. Your alveoli is like the yes, same here in sense. Okay, I know. It's okay. No worries. Just keep on listening slowly, and the things will happen. Okay. See, we as a teacher, like me and my FMG students, we are used to have the sessions of 6 hours, 10 hours, 8 hours. So we the students who are preparing for entrance, yes, Ankit, many students are of habit of listening and understanding and paying attention for 6 to 8 hours. Me, I can also teach for 10 hours, no problem. But since you all are in first year and you all are answering very nicely, I really appreciate that. It's okay if your capacity goes decreases after 3 hours, 3 to 4 hours. That's absolutely fine, no worries. So remember this relation: increase in surfactant increases inflatability, decreases collapsibility, increases compliance, and decreases work of breathing. So this creates an MCQ. Okay, this creates an MCQ here. So opposite will be decrease in surfactant decreases compliance, increases work of breathing. This was asked in exam. This question was asked in exam. So that's why I keep on asking how many FMG students are there in my class right now, because I knew that any other student from a regular college would not be able to stand so long to be able to understand the lectures for such a long duration. Only it's like you people who are FMG students can actually have a capacity to listen to me for 6 to 8 hours. Okay, that's why I have kept CVS, RS, CNS and kidney today, and the remaining topics like endo and GIT we can cover in 1 hour tomorrow. Okay, let us go to the 15th question. Respiratory distress syndrome, RDS, is caused due to lack of surfactant, is more common in premature babies, can be observed in adults also, all of the above. Very simple, very simple. Yes, Ankit. Ankit and Vivek are full of energy. Saddam is also full of energy. Okay. Yes, Bhumit. Very good. Very nice. Yeah, true. Very true. How did you find my session, all of you who are attending? Is it good? Is it because the student number has drastically dropped from morning to afternoon. We have started in the afternoon and now it is drastically dropped. Yes, the answer is D. All of the above. Yes. Ankit has replied, yes, it's going good. So I'm so happy. The session is going good. Only the thing is that the students with their capacity keeps on decreasing and they keep on leaving the chat box because there is no compulsion to sit on the mobile and to attend the sessions. So thank you Shweta, thank you for the appreciation. That's great. Okay, remember what is ARDS? ARDS, respiratory system, is because of decreased surfactant. Now surfactant are synthesized during the period of gestation, to be more precise in the somewhere in the 26th week. So what happens if there are chances of premature babies, then they may be having less amount of surfactant, and which can be cause of ARDS. Also in adults, because of certain conditions, the surfactants are getting damaged and that also causes RDS. So yes, all of the reasons can be possible for ARDS. Yes, all of the following is true about compliance except one thing is false about compliance. What do you think? Compliance of the lung plus thorax is 110 ml of centimeter of water pressure. Compliance of the lung is 220 ml centimeter of water pressure. Compliance of the work is delta V upon delta P upon 2. Compliance of the lung increases in fibrosis of the lungs. Yes, type 2 alveoli, type 2 pneumocytes, type 2 pneumocytes. Yes. The answer here is yes. Can you tell me what is the answer here? Compliance of lung plus thorax is 110 ml plus centimeter of water. No, that's a correct statement. This is a correct statement. This is also correct. C and D. The answer is between C and D. Yes, the answer is D. Compliance of the lung decreases in fibrosis. Decreases. It does not increases. It in fact decreases. Please remember, compliance of the lung decreases in fibrosis of the lungs. Rest all the three statements are very, very true. Very, very true. Okay. Coming to the next. No, not C, D. Compliance work. This is compliance work. Remember, compliance work and compliance is different. The answer is D. Okay, let us go to the 17th question. Airway resistance is more during inspiration than during expiration. Increases when the lung enlarges. Increases when the lung becomes smaller. Increases on sympathetic stimulation. What do you think the answer is for 17th question? True statement. You are going to find out the true statement. True statement regarding the airway resistance. Is it more during inspiration than during expiration? It increases when the lung enlarges, increases when the lung becomes smaller, or increases on sympathetic stimulation. Yes, that's Manish. Tendency to collapse increases for 16th answer. Remember, the 17th, the answer for 17th is B. Air resistance increases on sympathetic stimulation. It decreases on sympathetic stimulation. The answer for this is D. The air resistance decreases on sympathetic stimulation. No, sorry. Just wait. Air resistance. This is only true statement. Rest all are false statement. This is the false statement. Is more during inspiration than during expiration? No, air resistance is less during inspiration and more during expiration. Air resistance increases when the lung enlarges. No, it decreases when the lung enlarges. Air resistance increases when the lung becomes smaller. No, it decreases when the lungs become smaller. The answer is D. Air resistance increases on sympathetic. Only this is the statement. This is the false statement. This is the false statement, and this is the false statement. Even I am getting tired. Sorry. See, all these three statements are false actually, because the resistance is less during inspiration, not during expiration. Second thing is, it decreases when the lung enlarges, and it decreases when the lung becomes smaller. Yes, the answer is D. D. The answer is D. Answer is D here. Yes, please. Yes, 17th answer is D. Vishakha, Shabnam, D. 17th can't be answered. We have to find out the true statement. We have to find out the true statement here. Alright. So let us go to the next question. A lack of normal surfactant resulting. Now this is again thing we have which I have answered. A lack of normal surfactant results in increasing lung compliance. No, it will decrease in lung compliance. Stabilization of alveolar volume. No. What do you think is the answer for 18th question? Yes, what do you think is 18th question? We have just discussed about surfactants here. A lack of normal surfactant results in an increase in lung compliance, stabilization of alveolar volume, an increase in recoil tendency of the lungs, or all of the above. Yes, increases the recoil tendency of the lungs. That's a perfect answer. It increases the recoil tendency of the lungs. A lack of normal surfactant results in, yes, increasing the recoil tendency of the lungs. That's perfect. That is absolutely perfect. Absolutely fine. Okay. Primary defect in respiratory distress syndrome is. Primary defect in respiratory distress syndrome is weak inspirative muscles, hypoventilation. This is again repetitive question of the first one. Primary defect in respiratory distress syndrome is, what do you think is the answer? Weak inspiratory muscles, hypoventilation, reduced surfactant, or increased compliance. ARDS, very common. The answer is reduced surfactant is the most common defect in the ARDS, acute respiratory distress syndrome. Yes, 18C and 19 also C. 18 also C and 19 also C. Yes. Yes, absolutely. Everybody's charged up now. That's great. That's great. Okay. An increased airway resistance is caused by all of the following factors except. Okay. Increased air resistance, everything will increase except one: increase in lung volume, aging, chronic bronchitis, bronchial asthma. Yes, what do you think is the answer for 20? Yes, premature baby can be one of the best example of ARDS. Increased air resistance is caused by following factors except one factor which does not cause increase in the airway resistance. C. Chronic bronchitis. We have just discussed one point, forceful inspiration or increase in lung volumes. Yes, yes. Air resistance decreases when the lung volume increases. So only this is the factor except lung volume will decrease. The answer is A. See, an increase in air resistance is caused by all the following except aging, increases lung volume resistance, chronic bronchitis increases lung resistance, bronchial asthma always increases resistance, but increase in lung volume will decrease the airway resistance. So A is the answer here. It's a quite more of technical or grammatical question here. Okay, it's more of a grammatical question here. And increase in the lung volume decreases the airway resistance, and that's what the thing we have to answer. What we are going to answer here is there are three things which increases airway resistance and one thing which decreases airway resistance, and we have to answer that one thing which decreases airway resistance. So answer is A. Yes, answer is A. Yes sir, it's to 21 question number. How come 21 we have not started yet? Volume of the gas in the lungs at the end of normal expiration is. Okay, very good. Kesar has answered in advance. That's great, Kesar. 21, question number 21, the answer is at the end of normal expiration there are two volumes which are left in the lungs, ERV and RV, because when you talk about normal breathing, then normal expiration, and then like this. So this is ERV and this is RV. So there are two lung volumes which are left here, ERV and RV, which is together known as FRC. So the answer is B, functional residual capacity. For 21 the answer is B, functional residual capacity. Yes, absolutely right. Absolutely right. Everyone is absolutely right here. Okay, we are coming to an end of, I think, chapter. Yes, that's great. Residual volume of the lung increases. Residual volume of the lung increases in chronic obstructive lung diseases, in restrictive lung diseases, in fibrosis of the lungs, all of the above. What do you think for 22 would be the answer? Yes, what do you think of the answer for 22 would be? Yes, what do you think the answer for 22 would be? All the three things they increase: residual lung volume, restrictive lung diseases, fibrosis of the lungs, chronic obstructive bronchitis. Yes, very true. Yes, in all the three things the amount of air remaining in the lungs increases, because in obstructive lung diseases there is obstruction of the airways, so the air in the lungs also remains very high number. Restrictive lung diseases also the person is unable to throw out all the air, so relatively the residual volume increases. In fibrosis of the lungs, the alveoli collapse very soon, because they collapse very soon, the air left in the lungs is high. The answer is D, all of the above. In all of the conditions the residual volume of the lung increases. Yes, Vivek, the answer is D here. The answer is D. 23, very interesting question. J receptor. J receptor are present in walls of the alveoli, pulmonary capillary walls, wall of trachea, pulmonary interstitium. Yes, what do you think is the answer for 23rd? Yes, what do you think is the answer for 23rd? J receptors are present in walls of the alveoli, pulmonary capillary walls, walls of trachea or pulmonary interstitium. Yes, absolutely right. Yes, Mohammad Javed, absolutely right. It is pulmonary interstitium. Pulmonary interstitium is the area where the yes. Yes, Shabnam, maybe D. Yeah, maybe D in a sense. There is a confusion, but D is the, because there are two things which are right. So when the two things are right, you should go for D option as the right answer. Alright, yes, Shabnam, remember, when there are two options which are falling right, then you should go for always option D, all of the above. Okay. So 23rd, for 23rd the answer is D. For 23rd question the answer is D. Pulmonary interstitium, where is it located? See, alveoli and capillary. So J receptors, they are located in the interstitium of the lungs and they carry the impulse to the respiratory center via 10th cranial nerve, via vagus nerve. And when J receptors get stimulated, when their stimulation occurs, remember their stimulation of J receptor causes J reflex. And there are three important properties of J reflex. There are three important things of J reflex. No, they are present in the interstitium. Pulmonary interstitium is the best suitable answer here, Sharman. Not actually in the capillary wall. They are present in the interstitial areas. Why? Let me explain you this thing. See, the J receptors, they don't work normally. They only work when there is a pulmonary edema. When there is a pulmonary edema, in the edema there is accumulation of fluid in the pulmonary interstitium. When the fluid in the pulmonary interstitium increases, see, J reflex occurs when there is a cause of pulmonary edema because of any of the reasons. And pulmonary edema, the interstitial space increases, and because interstitial space increases, the diffusion of the gas decreases. The diffusion of the gas decreases, and because the diffusion of the gas decreases, the J reflex causes three things, and those three things are: number one, it causes tachypnea. Increase rate of respiration. Tachypnea, increase rate of respiration, so that more amount of air should come into the lungs, alveoli. Okay. And bradycardia, decrease blood pressure. Blood pressure should decrease. Okay, bradycardia. And the third thing is it causes yes, tachypnea, bradycardia and hypotension. Okay, there are the three important reflex of J reflex: tachypnea, bradycardia and hypotension. Remember these 3 points. Very interesting, because J reflex, their job is to cause more air to diffuse. See, when there is a pulmonary edema, less amount of the air diffuses. So the aim of the lungs is that more amount of air should diffuse. So to cause the more amount of air to diffuse, number one, it causes tachypnea, so that more amount of air can be breathed in. More concentration, more the diffusion. Second thing, bradycardia, so that the blood flow should become slow to the lungs and the alveoli, so that maximum amount of oxygen can be carried. Okay, bradycardia decreases the blood flow velocity also, and that causes the overall blood to stay in the lungs for longer period of time, and that causes maximum saturation with oxygen. and hypotension, so that blood pressure also decreases. Okay, so the answer is pulmonary interstitium. Yes. Pulmonary capillary wall, I have very rarely seen any of the books answering that thing. Okay, no problem. We'll definitely see to it again. Yes, Mukesh. Oxygen dissociation curve shift to right in all of the following except. Oxygen dissociation curve shift to right in all of the following except means one thing will cause shift to the left. Okay, rise in temperature, fall in 2 dBg, fall in pH, increase CO2 content. Answer is very simple here. Answer is very simple. Yes. If you look at the O2 curve, the right shift is due to decrease in pH, increase in H ions, increase in CO2, increase in temperature, increase in 2,3 dPg. The left shift is due to increase pH, decrease H ions, decrease CO2, decrease temperature, and decrease 2,3 dPg. So the answer is right shift. Temperature right shift, falling pH right shift, CO2 right shift. The answer is A. Yes, absolutely. Everybody's answer is right. Yes. Perfect. Okay. Going to the last question. Yes. Which of the following is most appropriate diffusion limited gas? Yes. What do you think? Which of the following is the most appropriate diffusion limited gas? Yes, dear students. Which of the following is the most appropriate diffusion limited gas? Carbon monoxide, carbon dioxide, oxygen, or nitrogen? What is the answer for 25th question, dear students? Diffusion limited gas, the gas which never stop diffusing. See, what do you mean by diffusion limited gas? Suppose this is an alveoli and this is a blood capillary. The blood is moving through the capillary, right? And throughout the blood movement, the gas should keep on diffusing from alveoli to capillary. Should keep on diffusing throughout its transition. Should never stop moving. The gas should never stop moving, and there is only one gas which never stops moving. There is only one gas which never stops moving from alveoli to blood, and that is, answer is A, carbon monoxide. See, carbon monoxide, it binds very strongly to hemoglobin. Let us have some idea here. Let us have some interesting facts here. Okay, some interesting facts here. See, let me give a very interesting, because there are questions on this type of topic. When you talk about the gas as a diffusion limited gas, try to understand the concept here. The blood moves from an alveoli within 0.75 seconds. Okay, from A to B, the blood takes 0.75 seconds to move. Now what happens when a gas is moving from alveoli to blood? When a gas is moving from alveoli to blood, the gas gets saturated. The gas gets saturated in the plasma, and once the gas is saturated in plasma, it stops moving. But please look here now. When oxygen is moving, the oxygen goes from alveoli to interstitium to blood, and from blood it goes to RBC. Okay. Now within A, that is from 0 second to 0.25 seconds. How much? 0.25 seconds. The blood is almost saturated with oxygen. almost saturated with oxygen, further oxygen movement does not occur. So oxygen becomes your perfusion limited gas. Means oxygen will only move if you can increase the perfusion of the blood. Blood flow will be increased. Remember, please have to understand this point here. Oxygen within 0.75 second of transition time, within 0.25 second the blood is saturated with oxygen. The remaining 0.5 second is wastage. If the blood perfusion increases, movement of the blood increases, then the oxygen will start moving even to the after that. So oxygen is your perfusion limited gas. But when it comes to carbon monoxide, the carbon monoxide, it is so strongly binds to hemoglobin that the blood never saturates with CO. Blood never saturates. If the blood never saturates with CO, means CO will keep on moving at this point also, at this point also, at this point also, and this point also. At every point throughout the flow, the carbon monoxide will keep on moving. So CO will never stop moving from alveoli to blood. Hence, this is called as diffusion limited gas. So oxygen is a perfusion limited gas and carbon monoxide is a diffusion limited gas. Means CO will only stop moving if there is problem with diffusion, problem with the diffusion membrane. Then and then only CO will stop moving, otherwise CO never stops moving. I hope you got this point clear, everybody. Carbon monoxide will stop moving only if the diffusion, there is a problem with the diffusion of the membrane, otherwise CO never stops moving. Hence carbon monoxide is used to determine the diffusion capacity of the lungs. CO is also used to determine the diffusion capacity of the lungs. If you are asked that which gas is used to determine diffusion capacity of the lungs, then it is carbon monoxide is used to determine the diffusion capacity of the lungs. Now, suppose if somebody asks you, if you get an MCQ, what is the amount of dissolved oxygen? Amount of dissolved oxygen if oxygen is given at, if hyperbaric oxygen is given at 60% concentration, okay, at 2 atmospheric pressure, and the options are 0.9, okay, 1.8, 2.4, 2.7 ml. What do you think will be the amount of oxygen dissolved if you are giving 60% oxygen at 2 atmospheric pressure? What will be your answer? Please tell me. A, B, C and D. If hyperbaric oxygen is given at 60% concentration and 2 atmospheric pressure, I am going to give you a very good guru mantra by which you can actually guess the answer within 5 seconds. Within 5 seconds. Yes. Please answer this question. What do you think is the amount of oxygen dissolved if you are giving hyperbaric oxygen at 60% concentration, 2 atmospheric pressure? Yes. What do you think, students? Are you all there? See, let me give you the hint here. At normal atmospheric pressure, we breathe 20% of oxygen, that is 21%, at 1 atmosphere, and the solubility of oxygen is 0.3 ml of oxygen. So we take 20% as 1/5 of 100%, that is 1 atmosphere pressure as 1 and 0.3 as 0.3. So 1 into 0.3 gives you 0.3 ml of oxygen dissolved at 1 atmospheric pressure. This is the standard of your equation. Suppose if you take 40%, okay, 40% at 2 atmosphere and at 0.3 solubility, then 40 is 2 times of 20%, so 2 and 2 times atmosphere, so 2 into 0.3, 2 to the 4 and 4 to the 12, the answer will be 1.2 ml of oxygen. And suppose if you give 60% oxygen and 2 atmospheric pressure, then 60 is 3 times of 20, 2 atmospheric pressure into 0.3, so 3 into 2 into 0.3, that is 3 2s are 6, 6 3s are 18, 1.8 ml of oxygen can be dissolved. No, 3 2s are 6, 6 3s are 18. If you are giving suppose 80% oxygen at 4 atmosphere pressure, please tell me what will be the answer. Yes, no, can't be C, because 60% is 3 times and we are giving 2 atmospheric pressure, right? How much? 2. So 60 is 3 times of 20%, 2 atmospheric pressure and 0.3. 3 2s are 6, 6 3s are 18, 1.8 ml. The answer is B. And for this one, yes, 4 and 0.3. 4 4 is 16, 16 3s are 48. The answer is 4.8 ml. I hope you are getting the question here. Yes, Vishal, very right. Yes. Okay, let me give one more thing. One more equation to solve again. 100% oxygen at 4 atmospheric pressure. Now please tell me the answer. 100% oxygen at 4 atmospheric pressure. Please tell me the answer. How much will be the oxygen dissolved? Yes, please tell me. Yes, absolutely right, Money. And could you tell me for this one now? 100% is 5 times 4 atmosphere into 4 into 0.3. 5 into 4 into 0.3. What do you think is the answer? Yes, 6 ml. Very good. 6 ml is the amount of oxygen can be dissolved. It is a maximum oxygen, okay, which can be dissolved clinically. Under clinical practice, this is the maximum oxygen which can be dissolved. Yes. Chalo, I will give one more thing. Should you go? Should I give you one more calculation? Should I give one more calculation? 40% oxygen at 3 atmospheric pressure. 40% oxygen at 3 atmospheric pressure. Tell me for this one now. %40 oxygen at 3 atmospheric pressure. Yes, could you please tell me what is the answer for this one now? Last. You should be able to answer within 5 seconds. No. Yes, Ankit. What does this sign means? I'm not getting this sign. What does this emoji means, Ankit? You and Money use it a lot. 15 to 4 into 0.3. 50 by 50. 5 into 4 into 0.3. Yes. The answer is 2 into 3 into 0.3. It is 1.8. 2 3 are 6, 6 is 18. 1.8 is the answer. 1.8 ml. Yes. Now you are all master. That's perfect. Now you all have become great master here. Okay. Now we are left with okay, who is this prototype 27? We have joined just now. Okay, it's a swag. Okay, so let us go for CNS. I think CNS is much interesting. We'll just solve the MCQs for CNS. Alright, just we'll solve the MCQs. Okay, at least we'll finish 3 chapters today. CNS will finish and then I will leave you. Okay, kidney, endo and GID, last 3 chapters tomorrow morning, 10 to 12, 2 hours. Okay, yes, is this okay? Is this okay for all of you? We'll just finish CNS and then I will leave you for today, and remaining things we'll do tomorrow. Okay, break. If I'll give break now, then nobody will turn up. Okay, study for 15 minutes. 9 o'clock we'll finish and we'll start tomorrow at 10. Is it fine, Money? Or shall we start at tomorrow at 10 only? Then we'll have to add 1 hour extra. Boku no Pico. Okay. CNS almost has 30 questions and kidney has almost 15 questions. What I will suggest is tomorrow morning you all meet at 10 o'clock, and 10 to 12 almost by 3 hours we'll finish off. Okay, within 3 hours we'll finish it off. Is that fine? Within 3 hours? Okay, so we will meet tomorrow at 10 a.m. and what I will do is I will create a new link, and okay, so 8 a.m. No, 8 a.m. is this is a break time, so 8 a.m. very few people will wake up at. So 9 a.m. fine. 9 a.m. tomorrow morning. What do you think? Tomorrow morning 9 a.m. is fine. What do you say, students? Yes? What do you all say? Tomorrow morning 9 a.m. is fine. Okay, so we'll meet at 9 a.m. and from 9 to 12 or 12:30 we'll be able to finish it. Okay. No, I can go for at least 1 or 2 hours more, Shweta. Frankly speaking, I can still go for 2 hours more. Okay. Acha, Vishakha is going for 10. How many of you are 10? Please type 10. And how many of you are 9? Please type 9. Let me have a voting for 9 or 10. Starting now. 9 a.m., 10 a.m. 2 options. Okay, many of our opinion of 10. Only 1 or 2 has gone for 9 right now. AV has gone for 9 a.m. but not all. Okay, so okay, 3 votes for 9. Max 4 votes for 9. Okay. 5 votes for 9. Money, typing 9 for 5 times is not giving you 5 times. Okay, see what we can do is 10 a.m. everybody is of 10 a.m. opinion, so we'll keep it at 10. Okay, so what we'll do is oh, Money has given quite entity. You are not in India, Money. Oh, okay, yeah, I forgot. Half an hour Russia and half yes, there's half an hour lag time. I was in Ufa and such places. So yes, 9:30 Indian time, 9:30 Indian Standard Time, and 10 a.m. Russian time. Is it fine? Thank you, Kesar. Thank you, Vishaka. So 9:30 Indian Standard Time. I will sit here 9:30, and it will be see 9 o'clock and 10 o'clock. We will just take a center point, and that is 9:30. So 9:30 is best, I think. Not too late, not too early. 9:30 to 12:30 we'll be able to finish everything. Okay, yes, 9:30 is fine. 9:30 I will start my class at Indian Standard Time at 9:30. So I think there will be time for you over there. Okay, so yes, thank you very much. And yes, I'm so happy that you all have been so patiently listening to me. Tomorrow session we will finish off CNS, renal system, GIT, and endocrine. These 4 sessions are left, and we'll finish off tomorrow in 3 hours, 3 to 4 hours. Okay, so see you all tomorrow. Bye bye. Thank you very much. Thank you all. Okay, thank you everyone. Bye bye. See you all. Have a good night. Stay home, stay safe. Thank you. Bye. Yes, bye bye. Thank you everyone. Have a good night. Thank you, Vishal. Yes, thank you, Vishaka. Thank you, Shweta. Thank you, Mani, Arjita, Maithili. Happy to see you all. Thank you. Have a good night. See you all. Bye bye. See you all. Bye bye.